There was only darkness at first. It was calm, cold, and quiet. Not a star, not a light, not a galaxy. There is only a thick soup of unseen particles floating in a void that is getting bigger. But in the middle of all that chaos, tiny ripples appeared. These were quantum shakes, which were only a proton wide, but would grow into galaxies. After billions of years, we can see the result. Beautiful spirals, huge ellipticals, and ghostly dwarfs spread out in a web-like pattern in space. But how did these huge buildings get built? What chain of events turned the shapeless gas we see through binoculars into the huge towns of stars we see now? This is the confusing, violent, and surprising story of how galaxies came to be. Let's start with the beginning, a quantum hiccup that changed the course of history. Quantum fluctuations to galactic seeds. There was chaos before there were galaxies, stars, atoms, or even light. There was only a quantum field writhing in space that stretched across a void that was expanding very quickly. But the confusion wasn't all over the place. Around 1/10 million trillion trillionth of a second after the Big Bang, the first moments of the universe that could be measured, microscopic quantum changes appeared. These were differences in energy density that are so small that humans can't see them. These were not errors, they were seeds. Inflation, the exponential expansion of space, acted like a cosmic amplifier. Those subatomic ripples were suddenly ballooned to macroscopic scales, frozen into the very fabric of the early universe. We can still see them today in the cosmic microwave background, CMB, as minute temperature differences are mapped by missions like WMAP and Planck. The bright spots, denser regions, gravitational wells, the dark spots, less dense. These variations were only one part in 100,000, yet they defined where everything would eventually gather. According to the LCDM model, lambda cold dark matter, these overdensities became the blueprint for structure. Gravity began to do its work, slowly pulling matter into clumps. But the matter involved wasn't just ordinary stuff. In fact, most of it wasn't even visible. Dark matter, which doesn't interact with light, made up the bulk of the mass in these early pockets. That made it a powerful attractor. As it coalesced under its own gravity, it formed deep potential wells. Ordinary matter, protons, neutrons, electrons, fell into these wells. But while dark matter clumped freely, ordinary matter had to cool first, shedding energy through radiation before it could form stars or galaxies. So in a way, dark matter laid the scaffolding, but the visible universe had to catch up. It's easy to see how this works in 3D with simulations like the Millennium simulation and Illustrista Eng. You can see how matter gathers into balls, how filaments form, and how gravity knots form, which are where galaxies finally catch fire. Also, guess what? Quantum fluctuations and simple physics are all that are used to start those models. That's how strong the idea is. It's mind-bending to think that these ripples were random. The Heisenberg uncertainty principle tells us that fluctuations in energy and position are unavoidable in a quantum system. In other words, the birth of the galaxies wasn't orchestrated by some grand design. It was baked into the laws of quantum mechanics. Even more interesting is that these changes happened just at the right size and in the right way. Galaxies would not have been able to form if they were too small for gravity to work against the growth of space. The world would have quickly turned into black holes if they had been too big. The conditions were matched in a way that cosmologists are still trying to figure out. Not all fluctuations grew at the same rate. After inflation ended, the universe entered a hot, dense phase known as the reheating era, where particles collided constantly. During this period, radiation dominated over matter. That radiation pressure resisted gravitational collapse, especially on small scales. Only large fluctuations, ones spread across vast regions, could begin to gather mass effectively. That's why the largest galaxies trace back to the biggest fluctuations, the heavyweight champions of the early universe. The Sloan Digital Sky Survey, SDSS, mapped over 1 million galaxies and showed how they cluster in patterns that match the predictions from those early fluctuations. This pattern, called the power spectrum, tells us just how much structure exists at different scales in the universe. And it all matches what we expect from inflation and quantum randomness. One of the most beautiful ideas in astronomy is that every star, planet, black hole, and beam of starlight we see today all came from a chance change that was smaller than an atom. That chaos, that noise, turned out to be the sign of how the universe is put together. Now, this process didn't happen overnight. From the time those fluctuations were frozen into the CMB to the formation of the first galaxies took hundreds of millions of years. But without those initial imperfections, without that quantum static, the universe would be smooth, boring, and dark forever. The dark matter scaffold. The universe's first unevenly dense seeds were made by the first quantum changes. Then, something else had to make those seeds into real structures. Dark matter was that something. Dark matter makes up roughly 85% of the matter in the universe, but it doesn't emit, reflect, or absorb light. We can't see it, but we can see what it does. And what it does is everything. Without dark matter, galaxies wouldn't exist. Stars would have nothing to cling to. The visible universe would still be a dim cloud of scattered hydrogen. Here's how it worked. In the early universe, ordinary or baryonic matter, things like protons and electrons, was tightly coupled to photons. This was the era of the photon-baryon fluid. Radiation pressure kept that fluid from collapsing under gravity. But dark matter didn't interact with photons. So while ordinary matter was stuck in a kind of cosmic tug-of-war, dark matter got a head start. It began forming structures, halos, on its own. These dark matter halos were like invisible gravitational wells. Imagine giant spherical nets in space, waiting to catch falling matter. As the universe cooled and photons decoupled during the era of recombination, about 380,000 years after the Big Bang, baryonic matter was finally free to fall into those wells. It's one of the most important phases in cosmic history, the moment when the blueprint laid down by quantum fluctuations began to fill in. Modern computer simulations have confirmed this in striking detail. The Millennium Simulation, one of the most ambitious cosmological models ever run, shows how dark matter alone can form vast, interconnected structures, the cosmic web. In these simulations, no visible matter is required to trace out the filamentary framework we see in real large-scale surveys. When astronomers later overlay real data from galaxy surveys onto these simulations, the fit is uncanny. So how did these halos form? It began with gravity. Small overdensities of dark matter started pulling in nearby particles. As they collapsed, their density increased, which in turn made them even more attractive. This runaway process is known as hierarchical clustering. Small halos form first, then merge to create bigger ones. An interesting fact is that some of these first halos were very small, even as little as the size of Earth. But they made way for ones that were much bigger. They were big enough to hold galaxies by the time the universe was a few 100 million years old. Dark matter halos had shapes and masses that told us a lot about the galaxies that would form inside them. Huge halos could attract and hold on to more gas, which would let big spiral or elliptical galaxies grow. Smaller halos had less gravity, so it was harder for them to hold on to gas, especially after powerful processes like supernovae started moving it away. That's one reason why dwarf galaxies often look so weak and bare. We have also directly seen the gravity signatures of these halos. Gravitational lensing, in which heavy objects bend and distort light from background sources, has been used to make a picture of where dark matter is found. Lensing shows that in galaxy clusters, huge halos surround not only individual galaxies, but also the whole cluster. The apparent matter is only a small part of the lensing strength. What about the rest? That's the dark matter that holds everything together, the scaffold. Even isolated galaxies offer clues. Stars orbiting in the outer edges of spiral galaxies like the Milky Way should slow down as you move farther from the center. If gravity were only coming from visible matter. But they don't. They maintain constant speeds, suggesting that an enormous unseen mass, dark matter, surrounds the entire galaxy like a protective cocoon. The halos formed before the galaxies did. That flips our usual logic. We're used to thinking of a structure forming first, then gaining mass. But in cosmic evolution, the mass, in the form of dark matter, arrived first, and the structure, the galaxy, came later. That's why we say galaxies live inside dark matter halos. New data from the James Webb Space Telescope, JWST, help us figure out how these halos formed in the beginning. JWST finds very faint high redshift galaxies, some of which formed less than 500 million years after the Big Bang, and uses the light and spread of stars to guess the size of the dark matter halos that hold them. These findings show that dark matter halos were not only around early on, they were also very important for galaxy formation at that time. One mystery that hasn't been solved is how dark matter acts on the smallest sizes. Dark matter may be warm or self-interacting, according to some models. This could change how small halos form and join. The usual cold dark matter model says the particles are heavy and move slowly. This model works well for large-scale structure, but has trouble understanding why dwarf galaxies are smooth and don't have the expected substructure. The cosmic web, filaments that feed galaxies. If you zoom out far enough, the universe stops looking like a sea of galaxies spread out, and it starts to look like something very biological. A huge cosmic spider web that goes on for billions of light years is what you'll see. At points where two long, bright threads of galaxies meet, they link like nerve cells. These are the building blocks of the universe that help galaxies grow, change, and even talk to each other. But this building is more than just beautiful to look at. It's important, because galaxies don't just form in a web, it feeds them. Let's rewind to the aftermath of recombination, about 380,000 years after the Big Bang. The universe was still mostly a smooth plasma, but tiny differences in density had started to snowball. Gravity began pulling matter toward the denser areas. Over hundreds of millions of years, that matter arranged itself into long, thread-like filaments. These became the scaffolding of the cosmic web. But here's the part most people miss. These filaments weren't just made of regular matter. They were primarily composed of dark matter, which meant their gravitational pull didn't depend on light or temperature. That made them perfect highways for baryonic matter, hydrogen and helium gas mostly, to flow into the nodes. Think of these filaments as intergalactic rivers. Gas doesn't fall straight into galaxies like rain. It flows along these filaments like water in a network of streams, converging at dense intersections where galaxies can form. These junctions, called nodes, are where dark matter halos become massive enough to seed galaxies, star clusters, and even entire galaxy clusters. You can actually see the structure of the web in real observational data. Projects like the Sloan Digital Sky Survey, SDSS, have mapped the positions of over 1 million galaxies. When plotted in 3D, their arrangement clearly outlines vast filaments and voids. It's not random, it's a map of the web in action. Simulations like Millennium and Illustris have taken this one step further. By putting in the science of gas and dark matter, they make a virtual world that is very close to the real one. In these models, gas moves down filaments, cools, and forms stars inside the tightest knots, just like galaxies actually form over cosmic time. Gas can't move without the web. Galaxies would not form until much later, and with a lot more trouble. What else does the web explain? It explains why galaxies often line up. Observations show that galaxies don't just move around randomly. Indeed, a lot of them spin along directions that are parallel to the strands in their area. That's because the gas coming into galaxies tends to come from certain directions, which are marked by the web around them. As gas moves in, it gives the expanding galaxy rotational momentum, which pushes it to spin in a certain direction. This filamentary gas inflow is especially important in the early universe. In high redshift galaxies, those formed less than 1 billion years after the Big Bang, we see signs of extreme star formation. These young galaxies are being bombarded with cold gas from the cosmic web, fueling what are essentially cosmic starbursts. That cold inflow bypasses the usual shock heating that slows down gas in modern galaxies, allowing star formation to proceed at a furious pace. Galaxies are still being shaped by the Webb. Huge structures like the Milky Way and the Laniakea supercluster are found along Webb strands that are still growing and changing. Galaxies in these filaments communicate with each other more often, join more often, and behave more dynamically than galaxies in cosmic gaps. But what about those empty places between strands which look like voids? They're not really empty, they're just not full. There may still be galaxies there, but they are likely to be smaller, farther apart, and change more slowly. This is because they don't have a steady flow of gas from the Webb. They are stuck in a kind of intergalactic desert, cut off from the intergalactic roads. More advanced telescopes like JWST and Euclid are now helping us map the Webb in greater detail and at earlier times. JWST, for example, can see galaxies at redshifts greater than 10, offering glimpses into Webb-fed star formation just a few 100 million years after the Big Bang. Meanwhile, gravitational lensing data from Euclid and the upcoming Vera Rubin Observatory will help trace dark matter filaments even where there are no visible galaxies. There's even an entire branch of study, cosmic cartography, dedicated to mapping and understanding the Webb. Scientists use tools like redshift surveys, weak lensing, and even machine learning to trace its shape and predict where galaxies are most likely to form. And increasingly, they're realizing that the Webb doesn't just explain where galaxies form, but how fast, how big, and how long they survive. How the cosmic Webb got its almost perfect fractal structure is still a mystery. General relativity models don't say that network will be so neatly made. It only shows up when you put together the mechanics of dark matter, quantum fluctuations, and the physics of gas cooling and feedback. One of the most beautiful things about the universe is how order can come from chaos. Why galaxies form at cosmic nodes? Not only are galaxies spread out along cosmic strands, but they also gather at certain high density points. These are the cosmic nodes, which are the universe's busy hubs. You can think of galaxies as pressure cookers for gravity, where dark matter, gas, and time all come together in just the right way to make something huge. The real question is why this is happening in this place and not somewhere else. Our answer lies in how matter moves, how dark matter halos behave, and the rules of gravity that guide how things fall apart. Cosmic nodes are the result of the large-scale structure of the universe collapsing along 3 dimensions. In a simplified view, imagine a sheet of dough being pressed in from multiple directions. Where all the pressure converges, you get a dense lump. That's your node. In cosmology, these are the regions where multiple filaments intersect, channeling enormous amounts of material into one spot. If filaments are rivers, nodes are deltas, where the flow converges and deposits everything it's carrying. Gravitational potential wells at these nodes are deep, thanks mostly to massive dark matter halos forming there first. In simulations like Millennium and Illustris TNG, these regions are clearly marked by extreme concentrations of dark matter. Gas naturally follows gravity, and in the early universe, it falls along filaments into the deepest wells, the nodes. As gas collapses and gets compressed, it heats up. If it can cool fast enough, stars begin to form, and just like that, a proto-galaxy is born. This node galaxy becomes a lot denser than galaxies in less dense areas, which is very interesting. The Sloan Digital Sky Survey, SDSS, says that galaxies that are in cluster environments, often at or near cosmic nodes, are bigger and older on average than galaxies that are in filaments or gaps. This isn't a mistake. Nodes create a high-pressure area with lots of gas, which makes it possible for stars to form quickly and furiously. In many cases, the gravitational chaos leads to frequent mergers. When 2 or more dark matter halos collide at a node, their galaxies often merge as well, fusing into larger, more massive systems. This is one reason elliptical galaxies are often found at the centers of clusters. The high frequency of mergers disrupts disk structures, leaving behind rounder, less ordered shapes. In addition, These merging help feed the enormous black holes in the center. When galaxies crash into each other, gas is pushed toward the center, which makes bursts of star formation and black hole activity. When a lot of gas is involved, this process is called wet merging, and it can make the galaxy and its center black hole grow very quickly. This is what led to the strong links we see today between the black hole's mass and the size of the galactic bulge. It is easy to see how this works in real life with the Coma cluster. It's a typical cosmic point. It's about 320 million light-years away. There are more than 1,000 galaxies in this area, and many of them are large elliptical galaxies. The cluster is at the point where several strands meet and send material into it. X-ray studies show huge amounts of hot gas, which is proof of the energy thrown into the system by galaxies fusing and feedback from AGNs. The temperature of gas in these nodes is also important. When galaxies fall into clusters, especially the hot, X-ray bright environments of big nodes, they experience something called ram pressure stripping. As they move through the intracluster medium, ICM, gas is blown out of the galaxy like wind through leaves. This can shut down star formation, transforming a once active spiral into a red and dead elliptical. That's why nodal galaxies tend to be older, with less ongoing star formation. Not all galaxies born at nodes die young. Some are shielded by massive dark matter halos that help retain cold gas. Others are constantly replenished by inflows from filaments, which can feed fresh material into the central galaxy. The competition between gas supply and environmental stripping determines how long a galaxy can keep forming stars in these high-density zones. The James Webb Space Telescope has recently begun to identify proto-clusters, ancient precursors to modern nodes, at redshifts greater than 7. One such structure, discovered in 2023, appears to be forming just 700 million years after the Big Bang. It already shows multiple massive galaxies coalescing at a filament junction, hinting that node-based galaxy formation began shockingly early. The biggest objects we know of are also found in cosmic nodes. Around these node crossings are built superclusters, such as the Laniakea supercluster, which is home to the Milky Way. Galaxies move into them not by chance, but because of the Webb's gravitational pull. Galaxies find the darkest wells, just like water finds the lowest point. That's where the real growth takes place. Proto Galaxies, the first clumps of light. The universe was a battlefield of unstable gas and dark matter that couldn't be seen before spiral arms spread out or galaxy disks spun. Not a star, nothing in place. Space is empty except for hydrogen, helium, and a blank sheet. That didn't last long, though. A change began about 200 million years after the Big Bang. Small groups of matter that were heavier than the rest of the space started to fall apart because of their own weight. These were not yet galaxies, but they were the beginnings of them. We call them proto-galaxies because they are hot, choppy clouds that show the first sketches of the universe's structure. The term proto-galaxy refers to any structure that's on the way to becoming a galaxy, but hasn't quite made it yet. These weren't pretty. They didn't have clean shapes, symmetrical arms, or well-defined cores. Instead, proto-galaxies were violent places, chaotic balls of hot gas and dark matter swirling around invisible scaffolds. Their defining characteristic was potential, enough mass and density to eventually ignite stars, form structure, and evolve into something more stable. How did these groups get there? It started with changes in density that were sped up by cosmic inflation. Over time, areas that were just a little heavier than usual started to pull in more matter, getting bigger and more gravitationally appealing. Dark matter took the lead and made the skeleton first. These places with too much matter made up the centers of what would become dark matter halos, and gas moved around them. Dark matter formed gravity wells deep enough to trap baryonic matter wherever it gathered. But gravity alone wasn't enough. Gas falling into a halo heats up through compression, reaching millions of degrees in larger halos. For stars to form, this gas had to cool, and cooling requires energy loss. In the early universe, that energy was shed mostly via atomic line cooling, as hydrogen and helium atoms were excited by collisions and then emitted photons as they relaxed back to ground state. If gas would cool faster than it was heated by compression or radiation, it collapsed into even denser regions, and star formation became possible. That first generation of stars, the so-called population 3 stars, were massive, short-lived, and composed almost entirely of hydrogen and helium. These were born inside proto-galaxies. Once the first stars ignited, they changed everything. Their UV radiation ionized the surrounding gas, their winds stirred up turbulence, and their eventual supernovae injected energy and heavier elements into the medium. This feedback cycle either triggered new star formation by compressing surrounding gas or shut it down by heating and dispersing it. What we see today in deep field observations from the James Webb Space Telescope, JWST, are snapshots of this era in real time. In 2023, JWST detected what appears to be a protogalactic system just 300 million years after the Big Bang, designated Sears 93316. This system is compact, intensely bright, and irregular, with light dominated by extremely young and hot stars. It's likely still in the process of assembling, merging with other protogalaxies, and carving out a more recognizable structure. Through projects like Illustris and Fire, we can see how protogalaxies are born in halos that are only 1 billion times the mass of the Sun. These constructions grow very quickly and aren't stable. There's a lot of chaotic gas inside that rotates unevenly and often falls and explodes. There are rounds of starbursts. Mergers happen a lot. In fact, the early universe was so dense that protogalaxies often smashed into each other, combined and ate each other within a few 100 million years. Low metallicity is one of the things that makes protogalaxies unique. In the field of astrophysics, a metal is anything heavier than helium. Since the first stars didn't last long enough to add these elements to the intergalactic medium, protogalaxies had almost pure gas. That meant cooling wasn't working as well, which made the process of early star formation less stable and more aggressive. Galaxies didn't start to form in more stable, metal-rich places until many generations of stars had died and recycled their matter. The transition from protogalaxy to true galaxy isn't marked by a clear line. It's a gradual process, more like adolescence than a birth. As stars accumulate, central masses grow, and disk-like features begin to appear. The system takes on the identity of a mature galaxy, but in its early protogalactic phase, it behaves more like a living experiment, constantly restructured by feedback, accretion, and collision. Some protogalaxies didn't work out. Not every group of gas and dark matter was able to hold on to its gas or make enough stars. Some were messed up by blasts close by, and others lost parts because of the tides from bigger halos. Some of these failed protogalaxies may now be very small dwarf galaxies that orbit bigger galaxies as leftovers from the universe's process of trial and error. In the local group, astronomers have found potential fossils of protogalaxies. Systems like Segway 1 or Bootes have extremely low metallicities and very small stellar populations, suggesting they were among the first galactic building blocks. Their simplicity, combined with age and chemical purity, makes them valuable time capsules, offering clues to the chaotic era of early galaxy formation. Population 3 stars and the first light. The universe flashed with a new kind of light that wasn't affected by time or galaxies. It was harsh, strong, and didn't have names. However, that glow wasn't from galaxies as we know them. It came from population 3 stars, the first generation of stars. These huge creatures from long ago started the first fires in the universe. Even though not a single one has been seen directly, their marks can be seen in every galaxy that came after. When we talk about star populations, astronomers split them into 3 broad types. Population 1, like our Sun, metal-rich and relatively young. Population 2, older metal-poor stars found in globular clusters and halos. And Population 3, the theoretical first stars, metal-free, massive, and born in a very different cosmos. Why does metal-free matter? In astronomical terms, metals mean anything heavier than hydrogen or helium. After the Big Bang, the universe was about 75% hydrogen and 25% helium, with a whisper of lithium. Heavier elements like carbon, oxygen, and iron simply didn't exist. And that made early star formation wildly different. Metals help gas clouds cool. Without them, primordial gas had to rely on molecular hydrogen for cooling, a far less efficient process. This meant the first collapsing gas clouds could only fragment into large clumps, not many small ones. The result? Enormous stars, some possibly reaching hundreds of times the mass of the Sun. These huge stars burned quickly and hot. It's possible that a population 3 star only lived a few million years before it went supernova or even went straight into a black hole. But in that short time, they did something very important. They made the first heavy parts. They made carbon, nitrogen, and oxygen through fusion. And when they died, they spread those elements out into the universe. This process is known as chemical enrichment, and it's the first step toward building complex structures like galaxies, solar systems, and life. Without population 3 stars, there'd be no planets, no DNA, and no you. How do we know they were real if we've never seen one? The evidence isn't straight, but it's strong. The James Webb Space Telescope, JWST, saw Glass Z13 in 2022. It is one of the farthest galaxies ever seen and is thought to be only 300 million years old. Its light pointed to a strange group of stars because it was very bright in the ultraviolet and had spectral signs that might be like what group 3 stars would make. Another clue comes from the metal-poor stars found in the Milky Way's halo. Some of these ancient stars contain only trace amounts of heavier elements, suggesting they formed shortly after a population 3 star went supernova. Enough time to inherit a small amount of metals, but not enough to match the richness of later generations. In 2005, astronomers discovered Xi 1327 to 2326, one of the most metal-poor stars ever found. With just 1/100,000th the Sun's metal content, it likely formed in a gas cloud barely touched by 1 or 2 population 3 explosions. Studying such stars is like sifting through cosmic ashes to reconstruct the first flames. Computer models have also been very helpful in learning about these prehistoric giants. Population 3 stars formed inside Minihalos, which are small balls of dark matter that weigh between 100,000 and 1 million times the mass of the Sun. These balls were used in models like the Renaissance project. They usually come out 1 or 2 at a time, and the strong UV rays and supernova feedback changed their surroundings in big ways. These stars did more than just shine brightly. They made changes. Their radiation set off the process of cosmic reionization, which broke up neutral hydrogen atoms and changed the early universe from dark and cloudy to clear and visible today. Reionization was like lifting a fog from the universe. It let photons move around easily and made it possible for galaxies to form today. But the legacy of population 3 stars goes even further. Some of them likely collapsed into black holes, possibly seeding the supermassive black holes we find at the centers of galaxies today. This solves one of astronomy's major puzzles. How did black holes grow so big, so fast? Starting with a 100 solar mass population 3 remnant makes that growth curve a lot more believable. Yet despite all this, no confirmed population 3 star has ever been observed. They were too massive, too short-lived, and too long ago. But their absence in modern skies isn't a disappointment. It's proof they did their job. They enriched the universe, paved the way for star formation to stabilize, and then disappeared, leaving only second-hand evidence. There's still hope, though. Telescopes like JWST, Extremely Large Telescope, ELT, and Nancy Grace Roman Space Telescope are designed to peer deeper into the early universe than ever before. By analyzing the light from the first galaxies and the stars within them, astronomers hope to catch a spectral signature that screams metal-free, the holy grail of cosmic archaeology. Supernova feedback as a trigger for collapse. In the beginning of time, the world wasn't made slowly, Galaxies were not made through calm, orderly crashes. They were made through fire, shock, and fury. Among the most powerful people who have shaped this cosmic chaos? Big bangs. The explosions that killed off huge stars didn't just end things. They sparked the start of a huge number of others. When a massive star, especially a population 3 star, reaches the end of its life, its core collapses under gravity. The outer layers rebound outward in a catastrophic blast, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. These supernova explosions inject enormous amounts of energy and material into the surrounding medium. This is called feedback, and in the early universe, it wasn't just destructive, it was catalytic. This is why, when gas clouds fall apart because of their own weight, stars are born. It can be hard to do this fall, though. For gas to squeeze even more, it has to cool down and lose energy. In a perfect world with few metals, that cooling doesn't work well. Here comes the supernova. When a star blows up, it sends shockwaves through the space between stars and between galaxies. These shockwaves squeeze nearby gas, which causes more collapses. As one star dies, its death sends shockwaves through space, shaking nearby gas clouds and giving them just the push they need to start collapsing into stars of their own. This process is called positive feedback, and it's very important for getting the first real star-forming areas going in and around young galaxies. But that's not the only thing supernovae do. They also add strong elements like carbon, oxygen, and iron to the environment. Because of this chemical enrichment, later gas clouds that are making stars will have minor metals in them, which will help them cool down more quickly. If it cools down more, gas falls apart into smaller groups, creating stars with less mass like our Sun instead of the huge, unstable behemoths of population 3. There's a fine balance, though. Supernovae can both help and hurt galaxy formation, depending on how much energy they release and the density of their environment. In dense regions, the shock waves might trigger multiple generations of star formation. In less dense environments, they can blow gas away entirely, quenching any future star formation, at least temporarily. In simulations like the Fire Feedback in Realistic Environments project, this duality is clear. Supernova feedback causes complex turbulence in early galaxies, sometimes driving huge winds of gas out into intergalactic space. These outflows can delay galaxy growth, suppress star formation, or even shape the structure of galaxies by redistributing angular momentum. A case from the Renaissance simulations, a group of detailed models of how galaxies formed in the early universe, shows how supernova feedback can create huge holes in the gas surrounding a proto-galaxy. These bubbles are tens of light years across and change the direction of material coming in, which changes how the galaxy looks in the end. The first galaxies might have died too soon, burned too brightly, or gone out too soon if these violent events hadn't happened. Observationally, the signs of ancient supernova feedback are hard to catch directly, but we see its results everywhere. In some of the most distant galaxies ever observed by JWST, like Sears 93316, researchers noted unusually bright compact starburst regions and massive outflows of ionized gas. These are telltale signs of recent large-scale star formation triggered by previous feedback episodes, likely involving supernova explosions. Even in our Milky Way, supernova feedback plays a vital role. Giant molecular clouds, regions like the Orion Nebula or the Carina complex, often show evidence of being shaped or compressed by older supernova remnants. The shock fronts from long-dead stars may be lighting the spark for new ones even now. The interplay between supernovae and early galaxies may also explain why galaxies didn't all grow at once. It created a kind of galactic pacing mechanism. Some star-forming regions were supercharged, while others got blasted apart and had to wait. This helps explain why some dwarf galaxies are still faint and irregular today. They may have had their early star formation shut down by overzealous feedback. A surprising discovery from the past few years is that there may be a link between supernova feedback and cosmic reionization. As hot, charged gas was thrown into space by these huge blasts, they may have helped ionize the universe by adding to the UV rays from early stars and quasars. Supernovae changed more than just galaxies in this way. They helped change the shape of the whole medium between galaxies. And the memory lives on. Supernovae-driven winds take metals from galaxies into the very large web of the universe. This makes metal-rich strands that other galaxies can use as food. This spreads the building blocks for planets and life far from where they were first made. Minihalos, the low-mass ancestors of galaxies. There were minihalos before galaxies got big, before spirals spread out across the sky and big groups caught satellites. In the beginning of the universe, these were the lightest things there were. They were small, dense balls of dark matter that quietly set the stage for the galactic era. They were not beautiful as they flew across the sky. A lot of them never even lit up. However, the first galaxies and stars would not have had a stage to act on without them. There are small groups of dark matter called minihalos that are about 100,000 to 100 million times the mass of the Sun. That may sound like a lot, but they're not even close to the tiniest dwarf galaxies we see now. But minihalos were everywhere in the early universe, only 100 to 200 million years after the Big Bang. They were made by the universe's first gravitational waves, which were caused by very small changes in quantum mechanics during the inflationary period. The first crucial point, minihalos were not galaxies, not at first. They were scaffolds, mostly invisible, but with enough gravity to gather gas. Whether they ever became true galaxies depended on several factors: their mass, temperature, and whether they could cool efficiently. Cooling is the most important part. As gas falls into a mini-halo, it gets hotter as it gets squeezed. It won't fall apart into stars if it can't cool down again. Atomic cooling didn't work well for early halos because they didn't have any metals. That only left one way, for molecular hydrogen to cool. But there is a catch. Molecular hydrogen is easily broken. It can be broken up by even weak ultraviolet light, so only the very first mini-halos, which didn't have any starlight, had the right conditions for H2 to cool down and make stars. This is why mini-halos are thought to be the first risk in star creation. Some did well. Most of them failed. When things went well, a few huge population 3 stars formed in the areas with the most thick gas. These stars were bright for only a few million years before they blew up as supernovae, but their birth set off a series of events. The reaction from these stars could blow all the gas out of the halo, which would stop the birth of any more stars. Or sometimes it squished nearby matter, which helped a nearby halo make stars in turn. But for many mini-halos, the story ends in silence. The first stars in the universe also produced Lyman-Werner radiation, a specific type of UV light that destroys molecular hydrogen. This background radiation spread through the cosmos like a wave, sterilizing thousands of nearby mini-halos and preventing further cooling. This is called radiative feedback, and it marked the end of widespread star formation in low-mass mini-halos. Yet they didn't disappear. Mini-halos that couldn't form stars still persisted as dark matter structures, orbiting larger halos, merging with others, or lingering as satellite subhalos around what would become Proto Galaxies. In modern simulations like Illustris and Elvis, exploring the local volume in simulations, we see the ghostly signatures of ancient mini-halos, still present today as ultra-faint dwarf galaxies or dark satellites with little to no visible matter. Some may never have hosted any stars at all. More and more people want to learn about these mini-halos because they might have something to do with dark galaxies, which are imaginary systems made mostly of dark matter and unseen gas. Even though we can't see them directly, they may leave marks on gas dynamics or gravity lensing patterns. Another fascinating implication, mini-halos may hold clues to the nature of dark matter itself. Their formation and survival depend heavily on the properties of dark matter particles. If dark matter is warm instead of cold, small-scale structures like mini-halos would be suppressed. Observing the number and distribution of these tiny halos could help narrow down the particle physics of the cosmos. Still, there are some secondary signs that they are here. There are a few very faint dwarf galaxies in the Milky Way's neighborhood that are likely the descendants of old Minihalos. Some are so dim that they only have a few hundred stars, but they still have a lot of dark matter in them. We would expect this very high mass-to-light ratio from early halos that only had a few stars form before they were stopped by feedback or effects in the surroundings. The James Webb Space Telescope, JWST, is also helping us probe deeper into this epoch. While it can't resolve individual mini-halos, it can detect clusters of faint galaxies from the universe's first few 100 million years. Some of these are likely formed within or near mini-halo structures, giving us a statistical window into their role in early galaxy formation. The role of cooling mechanisms in gas clouds. In the beginning of the world, gravity wasn't enough to make a galaxy. A thick cloud of gas and dark matter could collapse in on itself. But if the gas stayed hot, it wouldn't get tight enough to make stars. It got cooler after that. Cooling wasn't just a good idea, it was necessary. If not for it, gas would stay in a lukewarm state, unable to either collapse or spread out. Figuring out how gas cooled helps us figure out when and where stars and, finally, galaxies could form. When gas falls into a gravitational potential well, whether that is a dark matter halo or a growing proto-galactic structure, it heats up. Imagine a figure skater spiraling inward. The faster they spin, the more energy is generated. But in order to collapse further, that energy must escape. The gas has to discard its heat, quickly and efficiently. The universe's first and oldest way of cooling was through molecular hydrogen, or H2. In the early universe, there were no metals, so there were no atoms stronger than helium. That meant none of the more modern ways of cooling that we use today could work. The only way to get there was through molecular hydrogen. But hydrogen molecules are easily broken. They are slowly made, mostly through processes involving very few free electrons, and ultraviolet light can easily kill them. Still, H2 helped some of the first thick clouds cool down to a few hundred degrees Kelvin in early mini-halos, which are small areas of dark matter and gas. That might not sound very cold, but in the grand scheme of things, it was cold enough for stars to start forming. Once the first stars ignited and exploded, the environment transformed. Supernovae and the first hot stars flooded the cosmos with ultraviolet photons that easily broke apart molecular hydrogen. That forced the universe to rely on a new cooling system. Enter the atomic cooling era. In halos with virial temperatures above 10,000 degrees, Kelvin, atomic hydrogen and helium became the dominant cooling agents. These atoms could be excited by collisions and then emit light in specific wavelengths, like the classic Lyman alpha emission, allowing the gas to shed its energy and continue collapsing. This cooling mode dominated in slightly larger halos, with masses of around 100 million solar masses or higher, which emerged several hundred million years after the Big Bang. However, atomic cooling could only go so far. To form stars efficiently, gas clouds needed to fragment, to break up into smaller, denser pockets. And for that, the universe required something heavier, metals. In astronomy, metals refer to any element heavier than helium, such as carbon, oxygen, and silicon. These elements significantly improved cooling efficiency. They could absorb and re-radiate energy through fine structure transitions, allowing gas to cool down to just tens of degrees Kelvin. This advancement enabled the formation of the first low-mass stars, the predecessors of long-lived stars like our Sun. Additionally, the presence of metals allowed for the formation of dust grains, tiny solid particles. Dust became a cooling mechanism in its own right, especially in dense regions. It absorbed ultraviolet and visible light, re-emitted it in the far infrared, and even catalyzed chemical reactions on its surfaces. Dust cooling is the reason modern star-forming clouds can reach incredibly low temperatures, setting the stage for the creation of planetary systems. In massive galaxies today, we see a dynamic interplay of cooling mechanisms. In galactic halos, hot gas cools through a process known as Bremsstrahlung, or free-emission, as well as through collisional line radiation from metals. Within galactic disks, cooling is mostly driven by metal fine structure emission and infrared radiation from dust. The gas cooling efficiency depends on its density, temperature, metal content, and ionization state, all factors that determine how quickly a galaxy can form stars. But there's also a return process in space. It has been shown that as a galaxy cools down, it makes more stars and more supernova and black holes. These powerful events heat gas, cause leaks, and may stop more stars from forming if cooling systems don't stop them. This balance is particularly evident in galaxy clusters. At the centers of massive clusters, we observe cooling flows, regions where gas appears to cool rapidly, yet star formation does not keep pace. Why? Because a resident supermassive black hole pumps energy into the environment, reheating the gas just enough to prevent overcooling. This process is known as AGN feedback, and it helps explain why massive galaxies do not grow uncontrollably large. Recent observations from telescopes like James Webb Space Telescope, JWST, and Atacama Large Millimeter Submillimeter Array, ALMA, show streams of cold gas feeding into high redshift galaxies, those formed early in the universe. These streams remain cold and dense, avoiding the usual shock heating experienced by gas in modern galaxies. By staying cool, they feed young galaxies directly, enabling rapid growth faster than previously expected. As a result, cooling is more than just a physical process. It is what keeps stars from forming. It chooses when gas turns into stars, when halos turn into galaxies, and when galaxies grow or fade. The history of how stars were made is really the story of how well gas was able to cool down. At first, it did this with molecular hydrogen, then with atoms, and finally with metals and dust. Angular momentum, the spin that built spirals. If we look up at galaxies like the Milky Way or Andromeda, we often see beautiful spiral arms that move in a way that is hard to stop. That building is not a mistake. Angular momentum is the result of a cosmic force that goes all the way back to the beginning of the formation of galaxies. To put it simply, spin. Where did that spin come from, though? How did it change the huge range of galaxies we see today? In the early world, right after the Big Bang, the first seeds of angular momentum were planted. As gravity made matter gather together, the densities of different parts of space were slightly different. These differences weren't made up for no reason. They were caused by quantum fluctuations that spread out across the universe during cosmic inflation. When these groups of matter started to fall apart because of gravity, they didn't fall apart in a perfectly straight line. Instead, small imbalances and tidal forces between clumps next to each other caused torques, which are basically cosmic bends. This process is known as the tidal torque theory. Two or more nearby overdensities exerted gravitational pulls on each other. Those interactions induced a spin on the collapsing gas cloud. The more massive and asymmetric the neighboring structures, the stronger the torque, and the faster the proto-galaxy began to rotate. Over millions of years, that angular momentum was conserved, and as the cloud collapsed, it spun faster and faster, just like a figure skater pulling in their arms. But this spin wasn't evenly distributed. In the densest central regions, the gas often lost angular momentum through friction, collisions, and interactions with stars or dark matter. This allowed the gas to collapse further and form a galactic bulge or a central black hole. Meanwhile, the outer layers of gas retained more angular momentum, spreading out into a rotating disk. The result? A classic spiral galaxy, with a dense core and wide spinning arms. This spin prevented gas from collapsing directly into the center, forcing it to settle into orderly orbits around the galaxy's axis. The degree of spin, measured by a quantity called the spin parameter, ultimately helped determine whether a galaxy would become a spiral, an irregular blob, or something in between. Simulations show that halos with high spin parameters make disk galaxies that are thin and spread outward, while halos with low spin parameters make systems that are more compact and often irregular. But spin doesn't tell us everything. Also, the setting is important. When galaxies form in areas that are already crowded and where mergers happen often, they may quickly lose or shift their angular momentum, which can stop disk formation. Separated galaxies, on the other hand, are more likely to keep their original spin and form stable spiral patterns. Observationally, we've seen this play out. Using data from large sky surveys like the Sloan Digital Sky Survey, astronomers have found that spiral galaxies tend to reside in lower density environments. These are the cosmic suburbs, regions of the universe where mergers are rare and galaxies are free to evolve gently. Elliptical galaxies, on the other hand, are often found in clusters, where violent interactions have stripped them of their disks and scrambled their stellar motions. It's interesting that the rate at which stars form can be affected by how fast a galaxy spins. A process known as density wave theory says that gas tends to squeeze along spiral arms in disks that are spinning. These arms aren't real things. They're areas with a higher density that move around the disk like traffic jams on a round road. As gas moves through these heavier areas, it gets squished, which starts the process of stars forming. Spiral arms often look blue and bright because they are full of young, big stars that burn very quickly and hot. Angular momentum also plays a crucial role in the growth and feeding of central black holes. Infalling gas must shed angular momentum to reach the core. In many cases, bars, elongated features in disk galaxies, act as angular momentum sinks, funneling gas inward. This can ignite starbursts or feed supermassive black holes, shaping the galaxy's central activity. When rotational momentum is lost too quickly, on the other hand, like during a big merger, it can flip the disk over. The galaxy that results is less flat and more spherical, with stars moving in all sorts of directions instead of circling in a straight line. That's why irregular galaxies don't have the beautiful motion that spiral galaxies do. Trauma from the past has changed or erased their spin. Recent observations using integral field spectroscopy, like those from the mapping nearby galaxies at Apache Point Observatory, Munger project, have allowed astronomers to map stellar motion across thousands of galaxies. These maps reveal that while many galaxies exhibit orderly rotation, others have warped disks, counter-rotating cores, or signs of angular momentum misalignment. These features offer a fossil record of past mergers, gas inflows, and gravitational disturbances. In the worst cases, galaxies have been seen spinning in ways that don't make sense, either against the motion of galaxies around them, or even against their own dark matter halos. These strange events point to complicated evolutionary paths, which could include gas accreting from cosmic strands at odd angles, or late-stage mergers, with partners that rotate counterclockwise. Why some galaxies became elliptical early. These days, galaxies come in many forms, but the giant ellipticals are the biggest and most mysterious. Elliptical galaxies are circles of old stars that don't have any features. They are not like the beautiful swirls we think of when we think of star formation and motion. The strange thing is that many of them formed early, not late. We didn't expect that at all. How did these huge objects in space get so big and dead so quickly if spirals are young and well formed? In the early universe, roughly 1 to 3 billion years after the Big Bang, galaxies existed in a much denser cosmic environment. Space was more crowded, proto galaxies were smaller, and gravitational interactions were common. Major mergers, collisions between galaxies of similar mass, happened often, and each one had the potential to erase structure. When two spiral galaxies merge, their orderly rotation is shattered. Instead of preserving their disks, the stars are flung into random orbits. Gas clouds collide, compress, and trigger massive bursts of star formation, a starburst phase. But then, something odd happens. The rapid birth of new stars also releases powerful winds, driven by supernova explosions and radiation pressure. If the merger also triggers activity in the central black holes, causing them to accrete gas and light up as quasars, then even more energy is pumped into the surrounding medium. These feedback systems, which are powered by stars and black holes, can completely get rid of gas in the galaxy. It stops making stars when the gas runs out. The galaxy is quenched, and it turns into a swollen ball of stars with not much cold gas left. It stays that way. This is the usual way for a large circular galaxy to form. It's not the only one, though. Galaxy clusters started to form earlier and faster in dense protoclusters, which are areas that would later become galaxy clusters. The mass around them pulled on their dark matter halos, making them fall apart faster. These galaxies formed in places that were rough and had strong amounts of gas coming in. The gas didn't collapse into slow, ordered disks. Instead, it compressed in a chaotic way, creating tight, unstable systems that had early powerful starbursts. The James Webb Space Telescope has recently observed surprisingly massive red and compact galaxies at redshifts greater than 6. That's less than 1 billion years after the Big Bang. These galaxies already appear quenched, with little star formation. In one 2023 study, JWS detected a candidate galaxy at redshift 7.6 with the stellar mass of a modern elliptical and signs of an aged stellar population. If confirmed, it means massive galaxies were already done before the universe was even 1 billion years old. That not only makes us question our ideas about how galaxies evolved, it changes them. These early ellipticals must have been made by very efficient methods. It's possible that it happened through monolithic collapse, in which a whole ring of dark matter cooled quickly and stars were made all at once. Or they were made by merging quickly and many times, leaving behind a hot, starless mass. The atmosphere is also very important. Galaxies in busy places, like protoclusters, interacted with each other a lot. Even though these contacts didn't always cause full mergers, they could mess up spin and make turbulence. Minor mergers, in which a big galaxy eats a small one, also helped make star halos bigger and disks more unstable without killing them completely. Spheroidal systems were made over time by these repeating encounters. Observationally, we see evidence for this in today's universe. The largest elliptical galaxies tend to sit in the centers of galaxy clusters. They're called brightest cluster galaxies, BCGs. These giants have masses upwards of 100 trillion solar masses and show little to no ongoing star formation. Their stars are old, 10 to 13 billion years, and their shapes are round, lacking disks or spiral arms. Many have large cores with shallow brightness profiles, suggesting past black hole activity that scoured out central stars. This is backed up by simulations. It has been shown by big cosmological simulations like Illustris and Eagle that galaxies often lose their rotational momentum and fail to form disks when they join quickly in the early universe. The galaxies that are made are round and very hot, just like the ellipticals we see. Another clue comes from stellar kinematics. Using integral field spectroscopy, astronomers can map the motions of stars across galaxies. In ellipticals, these motions are random. There's no dominant rotation axis. That's a smoking gun for merger-driven growth. By contrast, spiral galaxies show clear rotation curves, with stars orbiting around a central axis in a flat plane. There's also the role of dry mergers between galaxies that are already gas-poor. In later cosmic times, ellipticals often merged with other ellipticals. These mergers didn't spark new star formation, but instead added bulk and random motion to the existing stellar population. This helped build the most massive ellipticals without changing their basic properties. It's important to remember that not all circular galaxies formed early. Some are the result of later mergers between circles that were in separate places. Big red dead galaxies that we see in groups, on the other hand, formed quickly and furiously when the universe was still young and wild. In short, elliptical galaxies are scars. They are the fossils of cosmic trauma. Where spirals tell stories of peaceful growth and graceful motion, ellipticals speak of chaos, of matter hurled together at high speeds, stripped of gas, and silenced. How gas accretion regulates galaxy growth. Galaxies are not fixed places. They are environments that change over time. At the heart of how galaxies change over time is a fight between fuel and feedback. Adding gas is what keeps this fight going. That's why galaxies die without it. When there is too much, they explode. Galaxies grow, shrink, or stop moving. To understand why, you need to know how they get gas from their surroundings and what they do with it. Where does this heat come from? Mostly the medium between galaxies. A huge amount of hydrogen and helium that was left over from the Big Bang can be found between galaxies. The spread isn't even, though. This gas moves along the strands of the cosmic web, which is the same structure that dark matter supports. As galactic roads, these strands guide cold gas into dark matter halos, which is where galaxies are born. In the early universe, this gas came in cold, and that's important. Normally, when gas falls into a gravitational well, it heats up through shocks. That's what happens in massive halos. But in low to intermediate mass halos, gas can stream in at temperatures below 100,000 Kelvin. That's cool enough for hydrogen to remain mostly neutral, allowing it to collapse further and form stars. This cold mode accretion is efficient. Simulations like Illustries, Fire, and Eagle show that most star-forming galaxies at redshift greater than 2, roughly 2 to 3 billion years after the Big Bang, grew primarily through this method. The gas flows in along filaments, spirals around the halo, and settles into a rotating disk. From there, it can condense into molecular clouds and begin forming stars. Some of it gets stopped at the halo boundary. In more massive halos, above roughly 10 to the 12th solar masses, the gas gets shock heated to several million Kelvin. This hot gas forms a stable atmosphere around the galaxy, often visible in X-rays. For this gas to contribute to galaxy growth, it must cool, a slow and inefficient process. That's why massive galaxies often grow more through mergers than through fresh accretion. Still, even hot halos can cool eventually. If the cooling time is shorter than the Hubble time, the age of the universe at that point, then gas can gradually rain down into the galaxy, fueling slow but steady star formation. On the other hand, recovered accretion is a halfway ground. Supernova blasts and stellar winds push gas back into the galaxy's halo when stars are born and die. This gas cools down and mixes with the medium around the galaxy. It can then fall back in, which is called galactic fountain recycle. Models of the Milky Way show that up to 50% of the gas that is making stars today belongs to a different age. Gas accretion also isn't smooth. It's clumpy, variable, and anisotropic. Sometimes entire dwarf galaxies fall in, bringing their gas along. Sometimes accretion happens through cold streams that penetrate hot halos, especially at early times. In 2022, a study using the Keck Observatory's MOSFIRE instrument detected evidence for a cold stream feeding a star-forming galaxy at redshift 2.5. The stream was rich in neutral hydrogen and aligned with the galaxy's rotation. Direct confirmation that cold mode accretion was fueling active star formation. But accretion doesn't tell us how much a galaxy grows by itself. Net growth, or how much gas comes in minus how much goes out, is what counts. How input fits into this picture is important. Star formation and black hole activity both generate outflows. These outflows can be fast, hundreds or even thousands of kilometers per second. In low-mass galaxies, outflows can exceed the escape velocity, permanently removing gas. In higher mass systems, the gas may remain gravitationally bound, but suspended in the halo, temporarily shutting off star formation. Feedback can also regulate the temperature of the circumgalactic medium. If active galactic nuclei, AGN, are pumping energy into the halo, they can maintain the gas in a hot state, preventing it from cooling and raining back in. This is one proposed mechanism for why massive galaxies become quenched. It's not that they lack gas, it's that they can't access it. The COS Halos study, which used the Hubble Space Telescope's Cosmic Origins spectrograph, discovered that even galaxies that have stopped forming new stars have huge amounts of charged gas stored in their halos. A lot of the time, these pools hold as much mass as the galaxy itself, but it's too hot and spread out for things to fall in. That shows that AGN and star feedback can lock away fuel, even if they can't get rid of it completely. As it turns out, gas buildup does more than just fuel growth. It also changes the structure. Which type of galaxy it is, spiral, elliptical, or irregular, depends on how gas enters it. Disks that spin are the result of smooth, uniform growth. When accretion is chaotic and not lined up right, it can cause thick rings, warps, or spheroids. The spin of the galaxy is determined by the rotational momentum of the gas coming in. Accretion is not only a driver, but also a shaper in this way. We also see cosmic downsizing at play. In the early universe, galaxies grew rapidly via cold accretion. Today, that mode has largely shut off. Most gas in modern halos is hot, and cooling is inefficient. Star formation rates have dropped by an order of magnitude over the last 10 billion years, not because the gas is gone, but because it's harder to access. Thick versus thin disks in young galaxies. People usually think of the Milky Way's beautiful spiral arms when they think of a galaxy. The Milky Way is a flat, tidy disk spinning in space. Evolution, on the other hand, took billions of years to get to that finished shape. Disk galaxies didn't always look so nice when they were young. They were thick, rough, and disorganized. A key part of figuring out how galaxies form is figuring out how they change from thick, jumbled structures to the familiar thin rings we see today. First, let's talk about what thick and thin mean. A thick disk is a part of the galaxy that has a large vertical range. Stars move above and below the center plane, often on orbits that are inclined. It is likely that these disks are older, have less metal, and are kinematically hot, which means that their stars move in a less ordered way. In comparison, thin circles are flatter, and the paths of the stars around them are almost circular. They usually have a lot of metals and are making stars right now. The Milky Way has both. Our galaxy's thick disk was likely established early, between 10 and 12 billion years ago. It's home to old stars, some nearly as old as the galaxy itself. The thin disk, where the Sun resides, is younger and still forming stars. But how did this double-layer structure form? And is it unique to the Milky Way? Let's go back to the beginning of the universe, which was around redshift 2-3, or about 11 billion years ago. At this point in time, galaxies were a mess. They were full of gas, shooting stars, and commotion inside. The Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, ALMA, have shown that many young galaxies had thick structures and odd forms. One explanation is violent disk instability, VDI. When a galaxy has a high gas fraction, more than 50% of its mass, the disk becomes gravitationally unstable. It forms massive clumps of gas and stars, each potentially 10 to the 8th or even 10 to the 9th solar masses. These clumps interact, scatter stars, and stir up vertical motion. The result? A puffy, turbulent disk. Simulations like those from the FIRE project show that feedback from these star-forming clumps through supernovae and stellar winds can also contribute to the thickening of the disk. The energy injected into the interstellar medium stirs the gas, pushing it vertically and creating a kinematically hotter environment for star formation. A part is also played by mergers. Minor mergers, in which a small satellite galaxy crashes into a bigger one, can heat the disk, making it puff up and sending stars into paths that are tilted more toward the disk. The Gaia satellite found proof of an ancient merger event in the Milky Way's thick disk history. This fits with what we already knew about the event. It's called the Gaia-Enceladusor sausage merger, and it happened about 10 billion years ago. Over time, as gas settles and mergers become less frequent, galaxies begin to calm. The gas fraction decreases, turbulence drops, and new stars are born into cooler, thinner orbits. This is how thin disks form, not by replacing the thick disk, but by building on top of it. This transition isn't uniform across all galaxies. Environment matters. Galaxies in dense clusters often have disturbed morphologies and truncated thin disks due to gravitational harassment and ram pressure stripping. Isolated field galaxies, on the other hand, have more room to grow stable, extended thin disks. Time is another part of it. It only takes a few billion years for the thick disk to form. Every so often, the thin disk will form over the next 8 to 10 billion years. It is thought that stars in the Milky Way's thick disk are more than 9 billion years old, while stars in the thin disk are younger. Chemistry supports this. Spectroscopic surveys like Apogee and Gala show that thick disk stars have higher alpha element abundances, a signature of rapid star formation dominated by Type II supernovae. Thin disk stars, which formed over longer timescales, show lower alpha abundances and more enrichment from Type Ia supernovae, which take longer to explode. This duality isn't just a feature of the Milky Way. The Sloan Digital Sky Survey, SDSS, and integral field spectrographs like MUSE have been used to look at edge-on galaxies and have found thick disk components in many disk galaxies. In some, the thick ring is not very clear. In others, it makes up most of the star mass. This shows that thick rings are a normal part of how galaxies form at the beginning. Why does this matter? Because the change from thick to thin is a big change in the structure. As a result, growth has gone from being disorderly to being ordered. Instability caused by gas moves to balance caused by stars. Astronomers use this shift to help them make models of how galaxies grow, how well feedback works, and how angular momentum changes over time. There are still open questions. For instance, how much of the thick disk is truly primordial, and how much is built later through secular processes? Can disks regrow after major mergers, or is a stable thin disk only possible through quiet evolution? Some galaxies, like lenticulars, seem to have lost their thin disks entirely, suggesting that environment and feedback can reverse the process. Feedback loops from starbursts. Starbursts are some of the most powerful and high-energy events that can happen in a galaxy's life. A galaxy makes stars at a much faster rate than usual during these events, sometimes hundreds or even thousands of solar masses per year. What comes after starbursts, though, is what makes them so important. Because these supernovae don't just make stars, they change the shape of the galaxies that gave birth to them. Starbursts set off feedback loops that can either help or stop the formation of new stars. These loops are made up of many complicated causes and effects. To understand how this works, imagine a galaxy undergoing a major inflow of cold gas. That gas condenses, collapses, and ignites a massive wave of star formation. The brightest, most massive stars form first, giants that burn hot, live fast, and die young. Within just a few million years, they explode as supernovae. These blasts don't simply mark the end of stellar lives, they mark the beginning of feedback. The energy from these supernovae, and from the radiation and winds of the massive stars before them, heats and stirs the surrounding gas. This creates a turbulent, pressurized environment in the galaxy's interstellar medium. In some cases, the gas is pushed outward in vast galactic winds, expelling material far beyond the galaxy's visible edges. This process can quench star formation by removing the very fuel it needs. In other cases, the shock waves compress nearby gas clouds, triggering even more star formation. This is the loop. Starbursts generate energy that either snuffs out or reignites the next generation of stars. Observations of galaxies like M82, the Cigar Galaxy, offer a vivid picture of this phenomenon. Located about 12 million light-years away, M82 is a classic example of a starburst galaxy. Its central region is ablaze with newborn stars and glowing gas, and it's launching a spectacular bipolar outflow of hot plasma, stretching tens of thousands of light-years above and below the disk. This outflow, visible in X-rays and optical emission lines, is the direct result of supernova-driven feedback. It has been shown by NASA's Chandra X-ray Observatory and the Hubble Space Telescope that these streams can carry very large amounts of mass, sometimes more than the galaxy is making stars. In other words, a galaxy like M82 is losing gas even faster than it is using it. which could mean that the flare ends before it should. In the worst situations, galaxies have stopped star formation for good because feedback pushed out their cold gas reserve. In some environments, especially in massive galaxies or those in dense clusters, expelled gas may eventually cool and fall back in. This is called a galactic fountain. The gas gets ejected, cools in the halo, and rains back down onto the disk. This cyclical recycling can regulate a galaxy's star formation, keeping it from running away too fast or dying off too soon. The balance between ejection and reaccretion is delicate, and models show it depends heavily on the galaxy's mass, the strength of the feedback, and the surrounding environment. It's not just supernovae that do this. During the early stages of a flare, stellar winds from big stars are very important. Streams of charged particles moving at hundreds or thousands of kilometers per second make up these winds. They can warm up and move gas around even before the stars die. When thousands of these stars work together, they make a pressure bubble that grows, shakes up, and changes the shape of the interstellar medium nearby. Then there's radiation pressure, particularly in dusty galaxies. The light from young stars gets absorbed and scattered by dust grains, exerting pressure that can blow cavities in gas clouds and help launch large-scale outflows. This is especially important in ultra-luminous infrared galaxies, where dust content is high and radiation pressure becomes one of the dominant feedback mechanisms. Modern simulations like those from the Illustris and FIRE projects incorporate all these forms of feedback: thermal, kinetic, and radiative. These simulations show that without feedback, galaxies grow too fast and too big, forming far more stars than observed. Feedback is what keeps the cosmic scales balanced. It explains why galaxies of different masses have such sharply defined star formation histories, and why many massive galaxies transition into quiescence relatively early. Interestingly, feedback loops don't just affect the galaxy that is breaking. Outflows can add metals and turbulence to the intergalactic medium when they form groups or clusters. This could affect local galaxies or the structure of the cosmic web on a bigger scale. These long-lasting effects show that starbursts are not one-time things. They are a part of the dynamic, linked process of development in the universe. Feedback can be both a break and a spark. When galaxies merge, for example, the strong shift in gravity pulls gas into the center, which starts an explosion. This burst can cause feedback that can squeeze other parts of the gas, spreading the fire outward. One wave of star formation fans the fire of another wave, making a burst that changes the shape of the whole galaxy. The black hole galaxy growth link. At first glance, black holes and galaxies look like two very different types of space monsters. Someone eats, one of them gives birth. If you zoom out and look far enough into the past of the universe, you'll find a strange link. The biggest galaxies often have the biggest black holes inside them, not by chance, but because they evolved together. This peaceful pairing in space makes me think that galaxies and their core black holes have grown together since the beginning, changing each other in ways that still stump astrophysicists. This relationship became undeniable when astronomers noticed a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, the dense spheroidal region of stars near the center. Specifically, the mass of the black hole is typically about 1/1000th the mass of the bulge. For example, the Milky Way's supermassive black hole, called Sagittarius A star, contains about 4 million solar masses, while the bulge around it weighs in at roughly 40 billion solar masses. The correlation holds across thousands of observed galaxies, from spirals to ellipticals, across a wide range of environments. It's one of the strongest and strangest correlations in extragalactic astronomy. The galaxy is very big, but the black hole is very small. How can something so small affect something so big? Power, not size, is the answer. Gas doesn't just disappear when it falls into an enormous black hole. In the accretion disk, that matter is squished and cooked to very high temperatures before it crosses the event horizon. That process turns mass into energy very quickly, up to 10% of the rest mass of the falling matter. Nuclear fusion in stars, on the other hand, only changes about 0.7% of the matter. There is a startling release of energy in the form of radiation and particles moving very quickly. Some of the biggest things in the universe, like quasars and active galactic nuclei, AGNs, get their power from this. That energy doesn't stay confined. It blasts outward, heating the surrounding gas, pushing it away, or even ionizing it entirely. This is known as AGN feedback, and it plays a central role in regulating star formation. When too much gas gets too close to the central black hole, the resulting energy can blow that gas back out into the galaxy's halo, or even eject it from the galaxy entirely. With less cold gas available, star formation slows or shuts down. In this way, the black hole becomes a thermostat, preventing the galaxy from overheating in terms of stellar birth. Observational evidence backs this up. X-ray and radio surveys show vast bubbles and jets of hot gas emerging from the centers of some galaxies, especially giant ellipticals and those in dense clusters. The Perseus cluster, for example, has enormous X-ray cavities blown into the surrounding hot plasma by repeated AGN outbursts from its central galaxy. These bubbles stretch tens of thousands of light-years and carry energy far beyond the black hole's immediate neighborhood. This feedback mechanism is so influential that modern galaxy formation models cannot reproduce the real universe without it. Simulations like Illustris and Eagle show that without AGN feedback, galaxies become unrealistically massive and blue, forming stars long after they should have shut down. Including black hole feedback, on the other hand, helps match observed galaxy populations in size, shape, and color. It's a cosmic check and balance system, growth regulated by destruction. But there are two sides to the connection. In the same way that black holes can stop galaxies from growing, galaxies also feed and form black holes. When galaxies merge, the gas is pushed toward the center, which can cause both starbursts and fast black hole growth. The two processes look like they are linked. We sometimes see galaxies that are going through both active black hole accretion and strong center star formation at the same time. This points to a shared source: gas flows caused by changes in gravity. One amazing example can be seen in quasar-host galaxies, which are galaxies with black holes that are actively eating and glowing across the electromagnetic spectrum. Deep pictures taken by the Hubble Space Telescope show that many of these hosts have recently merged or been distorted by tides. The gas was probably stirred up by these events. Some of it went into the black hole's core to feed it, while other parts went out into the universe to form stars. The two growth tracks show that the cause was the same. Yet, the details remain murky. Not every galaxy with a big bulge has a quasar, and not every active black hole resides in a merging system. There's a diversity of pathways to growth, and scientists are still unraveling how feedback operates over billions of years. Does black hole feedback act in sudden bursts, or in a more gentle, ongoing mode? Does it always quench star formation, or can it sometimes trigger it by compressing gas clouds? These questions drive much of today's research in both observations and simulations. Astronomers have found black holes millions or even billions of times the mass of the Sun in earlier times, less than 2 billion years after the Big Bang. This brings up a very important question. Did black holes form first, and then galaxies formed around them? Maybe galaxies formed first, and then black holes grew in the middle of them. There is proof for coevolution, but there is still disagreement about the order of events. Bar formation in disk galaxies. If you think of a galaxy, you probably picture a beautiful spiral shape with arms that spread out like bands and stars thrown all over the stage of the universe. Take a better look. There is something else in the middle of many spiral galaxies, like our own Milky Way. A bright, long structure of stars that cuts through the middle like a cosmic beam. This is a bar in space. It's also useful, not just pretty. A galaxy's past, present, and future are all shaped by this powerful force. Galactic bars are more than pretty structures, they're engines, These elongated collections of stars and interstellar material rotate in sync with the inner parts of the galaxy and act as a gravitational lever, redistributing matter and angular momentum across the disk. About 2/3 of all spiral galaxies, including the Milky Way, are thought to be barred spirals. That statistic alone hints at their evolutionary importance. Bars don't just happen. They emerge as a consequence of internal instabilities in a rotating disk and can drastically alter the trajectory of a galaxy's development. As gas and stars orbit in a rotating disk, small perturbations caused by density variations or tidal influences from nearby galaxies can grow into more pronounced asymmetries. If the disk is sufficiently massive and dynamically cold, meaning its stars have orderly circular orbits, then a bar can form as the system tries to redistribute its internal energy. Once it emerges, the bar becomes a conveyor belt, funneling material inward and outward depending on its orbital resonance with the disk. Moving gas around is one of the most important things bars do. It is possible for the bar's stretched gravity field to pull cosmic gas from the disk's edges toward its center, slowing it down as it moves. This center input often starts new waves of star formation, mostly around the nucleus. In ultraviolet and infrared scans, these places light up like bright knots of new stars. Some even turn into nuclear starburst rings, which are areas of high-level stellar activity that are squished by the kinetic pressure of the bar. In some cases, bars may also channel gas directly toward the central supermassive black hole. This creates an indirect connection between bar formation and active galactic nuclei. While the evidence is mixed, studies have shown that barred galaxies are slightly more likely to host low-luminosity AGNs, suggesting that bars can help feed black holes in quiet but persistent ways. But bars aren't just for moving things inward. They also help keep the upper parts of galaxies organized. Like spiral arms, pattern speed, which is the rate at which the bar turns, is often linked to spiral arms. Gravitational force from the bar can send density waves outward, which can make the spiral pattern stronger and more stable over time. In this way, the bar sets the galaxy's beat by controlling the movements in both the center and the edges. The longevity of bars is still a topic of debate. Some simulations suggest they are long-lived structures that can persist for billions of years, while others propose that they can dissolve or reform over time. Factors like gas inflow, dark matter halo shape, and even feedback from central starbursts or black holes can influence a bar's fate. For instance, too much central mass concentration caused by rapid star formation or black hole growth can weaken the bar's gravitational grip, leading to its eventual dissolution. This self-limiting behavior creates a feedback loop. Bars feed the center, but if the center gets too heavy, it kills the bar. Bars haven't always been so common, as we can see from looking back through cosmic time. The Hubble Space Telescope has shown that barred galaxies become more common in the more recent universe, around 5 billion years ago, or after redshift z equals 0.5. This means that bars probably form much later in the evolutionary process, after galaxies have grown up and settled into stable disks. Bars are less likely to form and stay in place in young galaxies, which are often rough and full of gas. In our own Milky Way, the central bar stretches over 27,000 light-years and rotates roughly once every 130 million years. It's thought to be responsible for funneling gas into the central regions, which may help explain the heightened star formation activity seen in the galactic center. The bar also interacts with the galaxy's spiral arms, creating resonances that shape the overall structure of the disk. Recent work using the Gaia mission's precision star maps has shed new light on the Milky Way's bar. Stellar streams and velocity fields in the inner disk show clear signatures of bar-driven dynamics, including a region known as the Hercules Stream, a group of stars whose motion is influenced by resonant interaction with the bar's pattern speed. These kinds of discoveries emphasize that the bar isn't just a visual feature, it's a living part of the galaxy's gravitational choreography. Even with everything we know, there are still a lot of secrets. Why do some galaxies not make bars at all? For what does the length or strength of a bar depend? How about when bars break? Can they be made again? These questions will help guide new findings as simulations get more realistic and studies look further into the universe. The transition from clumpy to stable galaxies. Astronomers don't see neat spirals or beautiful ellipticals when they look far into space, which means they're looking back in time a long time. They see a mess. High redshift galaxies, which are galaxies from the beginning of the universe, often look like cosmic train wrecks because they are bumpy, uneven, and turbulent. These galaxies, especially the ones that formed less than 3 billion years after the Big Bang, are clumpy in how they are built and how they act. But somehow, over time, many of these young, jumbled galaxies turned into the spirals and lenticulars we see in the sky today. Figuring out how this change happens is one of the most important questions in galaxy evolution. Clumpy galaxies are dominated by enormous star-forming regions, some of which are more massive than entire dwarf galaxies. These clumps form due to the gravitational instability of gas-rich disks. Early in the universe, galaxies were fed by cold gas streams funneled in through the cosmic web. This steady inflow kept their disks packed with low angular momentum gas, ideal conditions for fragmentation. Once these unstable disks reached a certain mass and density, gravitational collapse became inevitable. Giant clumps of gas collapsed rapidly, igniting intense episodes of star formation and creating short-lived but extremely bright stellar regions. These groups of things didn't stay put. They moved away. The huge clumps lost their rotational momentum and slowly spiraled toward the center of the galaxy. This is called dynamical drag. Moving inward wasn't just a change in how things looked. It changed the way things were built. As clumps came together in the core, they helped make bulges, made the inner disk thicker, and shook up the population of stars. In the long run, this stirring effect made the centers of areas more stable. It took a while to do. Based on computer simulations, this phase of clump movement and settlement could last up to 1 billion years. Observations from telescopes like the Hubble Space Telescope and ALMA, the Atacama Large Millimeter Submillimeter Array, have provided snapshots of this process across different epochs. For example, galaxies at redshift Z equals 2, roughly 10 billion years ago, show massive clumps with properties matching simulations of unstable gas-rich disks. In contrast, galaxies closer to redshift Z equals 0.5 or 5 billion years ago show smoother, more coherent disk structures. This gradual transition from clumpy to calm aligns well with what cosmologists call secular evolution, a process by which internal forces rather than mergers slowly reshape galaxies. A lot of early galaxies had minor mergers, which happened when small satellites fell into them and messed up their structure. In the early unstable world, this was almost certain to happen. Even though these small mergers didn't always kill galaxies, they did add new gas, stir up turbulence, and help make disks less stable. Over time, as the rate of mergers slowed down and gas started to come in more slowly, galaxies started to settle down. Disk galaxies started to take on familiar shapes when they were less affected by outside forces and had more time to change on the inside. A critical aspect of this transition is star formation regulation. In early clumpy galaxies, star formation occurred in bursts, driven by the dense clumps. But starbursts are unsustainable. Feedback from supernovae, stellar winds, and radiation pressure eventually heated and expelled gas, slowing star formation. This feedback didn't just impact individual clumps, it also contributed to the global stabilization of the disk. As the turbulent, gas-rich environment cooled and thinned out, star formation became more distributed and less explosive. The disk began to calm. As galaxies aged, their gas content changed. Cold gas reservoirs, primarily hydrogen, were depleted by ongoing star formation and not replenished as efficiently as before. Without a steady stream of cold gas, gravitational instabilities became less frequent. The result was a more stable, rotation-supported disk. In these environments, stars formed in thin layers and circular orbits, gradually building up the structured disks we see in mature spirals like the Milky Way. There is more than just obvious proof of this change. Kinematics changes can be seen in spectroscopic readings. Early clumpy galaxies often have unstable speed fields, with a lot of swirling and not much support for spinning. Later stage disks, on the other hand, have ordered rotation graphs that show disk settling and the conservation of rotational momentum. This change shows that a galaxy has grown up, going from being a wild child to a well-behaved adult. Even the vertical structure of galaxies changed. Young, clumpy galaxies typically had thick, puffed-up disks filled with random stellar motion. Over time, as clump-driven turbulence declined and gas inflow stabilized, these thick disks gave way to thinner, more coherent structures. In many cases, the original thick disk remained as an older stellar component, while new stars formed in a younger, thinner layer, a fossil record of galactic adolescence. The change wasn't the same for everyone. Some galaxies were never fully stable. Because their gravity wells were weak and they were sensitive to feedback, dwarf galaxies in particular often kept their irregular shapes. Others kept having problems because they were constantly being bothered in crowded places like galaxy groups. But for many systems like the Milky Way, this change was a turning point. It made it possible for spiral arms, bars, and other internal features that make up current disk galaxies to form. Raman pressure stripping in cluster galaxies. Galaxies can grow and change without much interruption when they are in the quiet, empty spaces of the universe. They can pull in gas, make stars, and spin without much trouble. The story changes a lot when you put a galaxy in the middle of a busy, dense collection of galaxies. In these cosmic cities, galaxies dive through seas of hot plasma and run into forces that take away the fuel they need to make stars. One of the most important of these forces is Raman pressure stripping, which is a violent process that stops stars from forming and changes the way galaxies evolve in groups. Raman pressure stripping occurs when a galaxy moves rapidly through the dense superheated gas that fills a galaxy cluster, known as the intracluster medium. This gas isn't visible in optical wavelengths, but it glows in X-rays and reaches temperatures of tens of millions of degrees Kelvin. As a galaxy barrels through this medium at speeds often exceeding 1,000 kilometers per second, it experiences a wind-like force. That force, known as Raman pressure, can be strong enough to push the galaxy's own gas out of its gravitational grip. It's a very simple matter of physics. The gas stays in place because of the galaxy's gravity until the pressure of the intracluster medium is stronger than the gravitational pull. Gas is taken away when this happens, especially in the galaxy's edges, where gravity is weakest. It can be like a high-speed blowtorch sending long tails of cold hydrogen, charged gas, and even dust into space. This isn't a slow leak. Because of how they look, astronomers call these features that stick out behind them jellyfish tails. Some of the best examples of Raman pressure stripping come from observations of the Virgo cluster, located about 55 million light-years from Earth. The spiral galaxy NGC 4522, for instance, shows clear evidence of gas being stripped from its disk. Its outer layers appear truncated, with no new stars forming there, while streams of hydrogen trail behind the galaxy. In the Coma cluster, even more dramatic cases exist, where entire galaxies have lost most of their gas and been reduced to starless red husks known as quenched spirals. Raman pressure stripping has serious consequences for a galaxy's life cycle. Gas is the raw material for star formation. Remove it, and the galaxy's ability to form new stars grinds to a halt. Over time, the galaxy fades, its blue young stars die off, and no new ones take their place. What remains is a redder, older stellar population, often arranged in a smoother, less defined structure. In fact, many of the elliptical and lenticular galaxies seen in clusters today are thought to be former spirals that were stripped, quenched, and aged by environmental processes like Raman pressure. The stripping is done in a certain order. First, the coldest gas on the outside is taken away. This is typically atomic hydrogen. It only takes a few 100 million years for this phase to finish. Then, heavier molecular gas from the inner disk can also be stripped off if the pressure is high enough or the galaxy's path takes it deeper into the cluster core. This is tougher to do since gravity holds the inner areas together more tightly. In some cases, it can even affect places where stars are being formed and parts of the galaxy bulge. The effectiveness of ram pressure stripping depends on a few key factors. One is the velocity of the galaxy relative to the cluster. The faster it moves, the stronger the pressure. Another is the density of the intracluster medium. Galaxies near the center of clusters feel more pressure than those at the outskirts. Finally, the galaxy's own mass and morphology play a role. More massive galaxies can resist stripping longer due to their deeper gravitational wells, while disk galaxies are particularly vulnerable due to their flat, extended gas distributions. It's interesting that ram pressure stripping can sometimes start star formation and then stop it. As the gas on the edge of the galaxy gets squeezed, it can fall apart into stars, which can cause a short burst of activity. This can be seen a lot in jellyfish galaxies, where the ends of the disk are shaped like bright knots of young stars. This phase doesn't last long though. The lights go out when the gas runs out. Astronomers have begun to map this process in real time using multi-wavelength observations. The Multi-Unit Spectroscopic Explorer, MUSE, on the Very Large Telescope has provided high-resolution velocity maps showing how stripped gas tails move relative to their parent galaxies. Combined with radio data from facilities like the Very Large Array, VLA, scientists can track the different phases of gas, atomic, molecular, and ionized, as they are peeled away and flung into the void. Ram pressure stripping is not just a passive consequence of being in a cluster. It is a key driver of the transformation of the galaxy population over cosmic time. Clusters are full of red and dead galaxies, precisely because so many once active spirals lost their fuel and aged into elliptical forms. This process helps explain why clusters have such a different mix of galaxies compared to the field, where isolated galaxies can remain gas-rich and star-forming for billions of years longer. This stripping is still going on in our neighborhood in space right now. As the large and small Magellanic Clouds move through the Milky Way's ring, they are starting to feel ram pressure. Hydrogen pollution studies have found signs of stripped gas following behind them. Even though it's not as exciting as when galaxies are close together, this shows that galaxies are always changing their surroundings, even when they're in the calmer outer space suburbs. The role of major and minor mergers. As they grow, galaxies don't stay alone. Galactic merger is the process by which they constantly contact, crash into, and change the shape of each other in the vast structure of the universe. It doesn't matter if two huge galaxies crash into each other or a much smaller one quietly merges in. Mergers are a big part of how galaxies change over time in terms of their size, structure, and behavior. It is important to understand these interactions, which are called major and minor mergers, in order to know how galaxies change over time to become the many different shapes we see today. A major merger occurs when two galaxies of roughly equal mass collide and combine. This isn't a gentle meeting. It's a cosmic car crash on scales that boggle the mind. Each galaxy brings its stars, gas, dust, and dark matter into the encounter. The gravitational interplay is intense. Tidal forces distort spiral arms, fling out massive tails of stars and gas, and stir the galactic disks into chaos. In the process, the original structures are often destroyed, and what remains is typically an elliptical or lenticular galaxy. This has been seen to happen in real time. There are many beautiful examples like the Antennae galaxies, which are 45 million light-years away. At the moment, two spiral galaxies full of gas are merging, creating huge loops of stars and causing a lot of new stars to form as their interstellar gas clouds crash into each other. Huge dust lanes, blue starburst regions, and long tidal tails are all signs of the impact that have been recorded in great detail by telescopes like Hubble. But these events are not rare exceptions. It seems that big mergers happened more often in the early universe, when galaxies were smaller and closer together. It's likely that many of the large elliptical galaxies we see today were made when two spiral galaxies joined together billions of years ago. When two big galaxies joined together, the black holes in the middle of them moved toward each other and finally joined together. Gravitational waves are ripples in spacetime that may be able to be picked up by the Laser Interferometer Space Antenna, LISA, which will be launched in the next 10 years. The violence of a major merger doesn't just scramble stars, it can also shut down star formation. As gas clouds collide, they create massive starbursts that quickly consume available fuel. At the same time, energy from the central black holes, now active quasars, can heat or expel the remaining gas, preventing future star birth. The result is a galaxy that ages rapidly, transitioning from blue and active to red and quiet. This process is called merger quenching, and it's a key way the universe transforms vibrant galaxies into silent, fossilized giants. In minor collisions, on the other hand, a big galaxy usually has a mass ratio greater than 3:1 and absorbs a much smaller galaxy. The big galaxy is like the host, and the small one is like a snack. Over cosmic time, these relationships are just as important, even though they don't look as exciting. One galaxy, the Milky Way, is in the middle of a small collision right now. It's eating the Sagittarius dwarf galaxy, a small satellite that's being stretched into a stream of stars as it goes around the Milky Way and breaks apart in its ring. Small deals happen quietly, but add up over time. A galaxy like the Milky Way can eat dozens or even hundreds of smaller galaxies over billions of years and get much bigger. This accreted matter often makes up the galactic halo, which is a large, faint group of stars that surrounds the disk of the galaxy. Astronomers can figure out the Milky Way's past of feasting by using data from projects like Gaia, and these stellar remains still have the chemical marks of where they came from. The difference between major and minor mergers also shows up in a galaxy's structure. Major mergers can destroy disks and form elliptical galaxies. Minor mergers, meanwhile, typically leave the main disk intact but can thicken it slightly and warp its shape. They can also deliver fresh gas, reigniting star formation in otherwise aging galaxies. In this way, minor mergers act as both builders and rejuvenators, adding mass, triggering stars, and shaping structure without total destruction. What determines whether a galaxy will experience a major or minor merger is mostly about location and timing. In dense environments like clusters, major mergers are rarer because galaxies move too fast to be captured by gravity. Minor mergers, however, are common because many small galaxies drift through the cluster and fall into the orbits of larger hosts. In the field, cosmic suburbs, where galaxies move slower, major mergers are more feasible, and some of the biggest collisions in the universe have likely taken place there. Simulations like Illustris and Eagle have shown how essential mergers are to galaxy evolution. These computational models follow billions of particles, representing dark matter, gas, and stars across cosmic time. They show galaxies growing not just through internal star formation, but through repeated interactions, each merger changing their spin, mass, shape, and activity. Without mergers, the galaxies we see today, especially the most massive ones, could not exist in their current form. The relics of past mergers are all around us. Shell-like features around ellipticals, streams of stars wrapping around spirals, double cores, warped disks. These are all the bruises and scars left by past collisions. Even our nearest neighbor, Andromeda, is showing signs of a recent merger. Its halo is peppered with streams and clumps of stars from galaxies it has consumed. In about 4 billion years, it will merge with the Milky Way in a colossal event expected to transform both galaxies into a massive elliptical. This future collision has already been dubbed Milkomeda. Ghost mergers, when galaxies collide but leave no trace. There aren't always fireworks, shows of stars, tidal tails, or twisted structures after galaxies crash into each other. Some leave behind almost nothing, no visual chaos, no big changes in shape. Just a quiet flow of gas, mass, or speed. These are called ghost mergers. and they happen in places with little light and gas, so the effects of the crash are hard to see. They happen more often than we thought. Traditionally, astronomers tracked galactic mergers by looking for visual clues: distorted arms, starburst activity, or multiple bright cores. But surveys using deep infrared and radio observations have uncovered galaxies that seem far too massive or centrally concentrated for their quiet visual profiles. Their shapes are smooth, their disks intact, and their surroundings calm. So how did they get that big? Stealth mergers. These are events where a smaller galaxy, often a dwarf or a gas-poor elliptical, merges with a larger one without causing significant disruption. No gas means no new star formation, and low relative mass means the gravitational impact is minimal. The smaller galaxy sinks in, its stars dissolve into the host's halo, and within a few 100 million years, all traces vanish. Ghost mergers also happen in the outskirts of galaxy clusters, where tidal stripping and long-term harassment have already weakened galaxies before they collide. By the time they interact, they're shells of their former selves. No gas, no structure, and little resistance. The merger becomes more of an absorption, a quiet assimilation. And unless you're tracking stellar population age gradients or subtle kinematic shifts, you might never notice. These kinds of mergers challenge our understanding of galaxy growth. Traditionally, we separated galaxy evolution into wet, gas-rich, and dry, gas-poor mergers. Wet mergers trigger activity. Dry mergers are quiet, but ghost mergers go a step further. They're so dry, so stealthy, that they barely leave a statistical footprint. Yet they matter. A study in 2021, using data from the Subaru telescope's Hyper-Suprime Cam, found that many massive elliptical galaxies at moderate redshifts showed size growth over time, but not the expected number of disturbed morphologies. The implication: much of their size increase could be due to minor, gas-poor mergers that escaped visual detection. Ghosts, essentially. The James Webb Space Telescope has begun to clarify this picture. With its sensitivity to mid-infrared light and ability to pierce through dust, JWST is uncovering low-surface brightness features that hint at ancient mergers, shells, streams, or compact companion remnants. But even then, it's a cosmic detective hunt. Some galaxies are so good at erasing their pasts that not even Webb can bring the scars to light. Ghost mergers have more than just structural effects. They also change where dark matter is found. The simulations show that even if no one sees the stars, a quiet merger can still add dark matter to a ring, making it heavier and stronger through gravity. That means a galaxy can get bigger, its potential well can get deeper, and its star formation processes can change slightly without anyone noticing. There's even a theoretical link to ultra-diffuse galaxies. Some researchers propose that certain ultra-diffuse systems in clusters may have been the victims of ghost mergers that stripped their stars without lighting up new ones. What's left behind is a puffy, low-density relic, with the mass of a dwarf but the size of a spiral, and an origin story that's invisible in optical light. We also need to know about ghost mergers for our cosmic statistics. We depend on visual signs of interactions a lot when we try to figure out how galaxies grow over time. But if a lot of mass buildup happens without being noticed, we might be wrong about how often galaxies join and how minor events affect the structure of galaxies. Why some galaxies stay irregular forever? At least that's what standard models of cosmic evolution say should happen. Galaxies should get older. At first, they are jumbled, off-center, and full of commotion, but over time, they settle into beautiful swirls or huge elliptical shapes. But some galaxies don't want to get older. Even after billions of years, they still look uneven, unorganized, and crazy. These are the irregular galaxies. The fact that they won't follow the cosmic plan shows how complicated and disorganized galaxy formation really is. Irregular galaxies make up a small percentage of the local universe, but they were far more common in the earlier epochs. The Hubble Ultra Deep Field, a telescope snapshot of ancient light from the early universe, shows that young galaxies often lacked the neat forms we see in nearby spirals or ellipticals. They were misshapen, clumpy, and constantly disturbed, signs of a universe still building its scaffolding. However, while most of these early irregulars eventually merged, evolved, or stabilized, some galaxies never made that transition. So why do some galaxies always stay crooked? The first important thing is mass. A lot of irregular galaxies are low-mass systems, which means they have a lot fewer stars, less gas, and a gravitational potential well that is much smaller. In easy words, they don't have enough weight to get themselves in order. It's hard to make sense of things when you're trying to gather a pile of leaves with no wind. These galaxies aren't strong enough to pull their gas into a stable spinning disk, and when outside forces or chaos stir the pot, they often can't hold on to their own material. Dwarf irregular galaxies, like IC 1613 or the Small Magellanic Cloud, are prime examples. These systems are small, often with stellar masses under 10 to the 8th solar masses. They contain rich clouds of hydrogen gas, scattered star-forming regions, and patchy distributions of old and young stars. Their shapes lack symmetry, and their star formation histories are erratic, bursts followed by lulls, driven by internal chaos or external nudges. When we talk about nudges, the second reason irregulars stay irregular is their surroundings. A lot of them live on the edges of bigger galaxies or float around galaxy groups. The construction of these areas is already very weak, and the effects of tides and ram pressure stripping make it even worse. Think of a small boat that is being tossed around by waves and currents. It can't stay still. Gravitational waves stretch and warp a small galaxy as it goes around a bigger one, like the Milky Way or Andromeda. This can cause bursts of star formation or tear the galaxy apart completely. But these effects don't always lead to assimilation. Sometimes they just keep the dwarf stirred up. Instead of merging smoothly or collapsing into order, these galaxies remain in a perpetual state of disruption. For example, the Sagittarius dwarf irregular galaxy is in the process of being cannibalized by the Milky Way, but it still shows signs of recent star formation and asymmetry. It's being eaten, but not gracefully. Feedback from the formation of stars is another factor. In galaxies with low masses, the explosion of a single supernova can blow out a lot of gas. When you add that up over a group of young stars, you get a loop that hurts itself. As the galaxy makes stars, those stars explode, sending out blast waves that stop the formation of new stars or completely eject gas. A solid disk or bulge doesn't form because of this irregular process. The galaxy keeps restarting, but it never gets to the point where it has enough mass and structure to change. Observations from instruments like Spitzer and ALMA reveal that many irregularities contain chaotic distributions of molecular gas and dust. Instead of smooth, rotating reservoirs, the gas is broken into clumps or scattered across different regions. Without orderly inflow, it's hard to sustain long-term star formation. And without steady star formation, a galaxy can't build up enough mass to stabilize itself through gravitational self-regulation. There's also the issue of angular momentum. Some galaxies never had much to begin with. Angular momentum, essentially the rotational spin a galaxy inherits from the cosmic gas cloud it formed in, is what helps flatten galaxies into disks. But if the primordial cloud had little rotation, or if it was disrupted early, the resulting galaxy might never form a disk at all. Instead, it becomes a lumpy, slow-rotating system that lacks the symmetry seen in spirals. A low metallicity means that the stars and gas in an irregular galaxy don't have many elements heavier than helium. This is another sign that their growth has stopped. Without metals, gas can't cool as well, and bad cooling means stars form more slowly, and there aren't as many ways for areas to collapse into heavier ones. This makes a structure that is less dense and spread out, and it doesn't easily collapse into ordered forms. Not all irregular galaxies are failures of evolution. Some are the remnants of disrupted mergers, large galaxies that were torn apart and have not yet reformed. Others are tidal dwarfs, born from the debris of other galaxy interactions. These systems can be metal-rich, but still chaotic, revealing that irregularity can come from both immaturity and trauma. A lot of irregulars are still working, even though they might look messy. Many of them are places where stars are being formed quickly and brightly with blue light from the new stars. Starbursts can happen because their gas stores are disorganized, they don't have any bending forces, and they interact with each other a lot. Some irregular galaxies shine brighter than more large galaxies in ultraviolet or infrared light because they have dense areas where stars are being born quickly. Some galaxies will always be irregular because of their mass, their surroundings, their past, and their luck. They didn't have the right materials or the right circumstances to grow into great spirals. They weren't big enough to cause the center bulge to form. Their neighbors pushed them around, feedback shook them, or they were born without enough spin. It means that they will always be the cosmic outcasts, messy and unexpected, but full of clues about how galaxies grow or don't grow. Galactic cannibalism, when the big ones eat the small ones. Not all changes in galaxies are peaceful. Some of it is very bad. In the cold, empty space, staying alive isn't just about getting bigger, it's also about outliving and eating everything else. Welcome to galactic cannibalism, the process by which big galaxies eat smaller ones, tearing their stars apart, swallowing their gas, and combining their dark matter halos like animals in an old forest. The term may sound sensational, but it's a real and well-studied mechanism in galactic growth. In fact, our own Milky Way has a history of cannibalism, one it's still acting out today. Let's start with Sagittarius, a dwarf galaxy first discovered in 1994, currently being shredded and pulled apart by the Milky Way's gravitational forces. Its stellar stream now wraps around our galaxy like tattered ribbons, slowly spiraling inward. We've even detected clumps of stars from Sagittarius embedded within the Milky Way's halo, silent testimony to a past meal still being digested. This is not a one-time thing. Not at all. Around big galaxies like the Milky Way and Andromeda are smaller galaxies called satellite galaxies. Some of these galaxies are in safe orbits, while others are already moving toward destruction. The paths of these planets break apart, and tidal forces stretch them out. They are torn apart over time, and the pieces that fall to the ground add to the disk, ring, or bulge of the mother galaxy. Andromeda, the largest galaxy in our local group, is even more notorious. It has consumed multiple dwarf galaxies over the past few billion years. Some of their remnants can still be seen in the form of ghostly star streams orbiting its massive body. In fact, a 2020 study using data from Gaia and Hubble showed that Andromeda's stellar halo is composed of the bones of at least a dozen former galaxies, making it the ultimate cosmic cannibal. Galactic cannibalism isn't just a dramatic flourish, it's a core component of hierarchical structure formation. In the lambda-cold dark matter model, lambda-cold dark matter, small structures form first and merge over time to build larger ones. That means today's massive spirals and ellipticals weren't always so big. They grew by eating their neighbors. But cannibalism also reshapes the victim. As stars are stripped away, some fall into the disk, but others form extended stellar halos, diffuse spherical regions surrounding galaxies. These halos are like archaeological dig sites, revealing a record of every meal a galaxy has ever consumed. In fact, much of what we know about the Milky Way's merger history comes from analyzing its halo composition, motion patterns, and metallicity gradients. The process affects star formation too. Sometimes, ingesting a gas-rich galaxy can reignite starburst activity in the host. The fresh supply of cold gas can collapse and form new stars, giving an aging spiral a burst of brightness. Other times, especially with dry, gas-poor mergers, the impact is structural, thickening disks, puffing up bulges, or transforming spirals into lenticular or elliptical galaxies. Cannibalism also plays a role in black hole growth. Many galaxies contain supermassive black holes at their centers, and when two galaxies merge, their central black holes can eventually collide, emitting powerful gravitational waves in the process. But even before that, the increased gas density from the infalling galaxy can feed the host's black hole, sparking periods of intense active galactic nucleus (AGN) activity. Still, this violent process isn't always easy to see. It can take hundreds of millions of years for cannibalism to happen. The victim may look whole for a long time, even though its insides are breaking down. We see tidal tails, weak star streams, or globular clusters that have moved. High-precision tools like Gaia, which tracks the positions and movements of more than 1 billion stars, are needed to show how big these ancient meals were. Projects like Illustris, Teng, and Eagle have modeled galaxy evolution over billions of years, consistently showing that massive galaxies accumulate much of their outer halo mass through minor mergers and cannibalism. In these simulations, galaxies grow not just by forming new stars, but by tearing others apart and taking what remains. It's a sad and beautiful picture at the same time. Galaxies are formed by time and force. Even the calmest spiral in the sky at night could be the graveyard for dozens of smaller ones. Their stars are still bright, but they are now overlawed by aliens and shine in their own sky. And the process isn't over. The Milky Way and Andromeda are on a collision course. In about 4 billion years, the two giants will merge. By then, they'll have consumed several more dwarf galaxies. Their eventual union will create a new elliptical galaxy, often referred to in simulations as Milkomeda, and that galaxy will continue the cycle, surrounded by smaller companions, slowly picking them off one by one. Gas-rich versus gas-poor birth environments. Hydrogen and helium, which are the universe's smallest and most common elements, make up most of the early galaxy supply chain. But this stuff isn't spread out equally in every part of the universe. It is possible to make bright, star-filled galaxies in places that are full of gas. Others don't have much gas to begin with, so their galaxies are starved before they even get hot. This split helps us understand why some galaxies do well, and others stop growing, fade, or never fully form at all. In the early times after the Big Bang, the world was mostly made up of hydrogen and helium ions. As the universe grew and cooled, these particles came back together to make neutral atoms. This made it possible for the first gas clouds to settle due to gravity. But the amount of gas that ended up in a certain area wasn't just a chance guess. It was shaped by both the original quantum changes and the cosmic web's large-scale gravitational structure. In gas-rich birth environments, matter was naturally drawn toward dense intersections of the cosmic web, gravitational wells carved by dark matter. These were the nodes where cold filaments funneled gas in from the surrounding universe. As gravity pulled the gas inward, it compressed, heated, and eventually cooled enough to ignite star formation. Galaxies born in these places had everything they needed: cold gas inflows, gravitational stability, and high densities. They lit up fast and bright. We see this pattern in early massive galaxies at high redshift, often referred to in studies using data from ALMA or the James Webb Space Telescope. Some of these galaxies, formed within the first 1 billion years after the Big Bang, are surprisingly large and structured. Observations reveal thick reservoirs of molecular hydrogen and dust, signs of intense and efficient star formation. These galaxies, like GNZ 11, are thought to have formed in regions where gas was plentiful and readily available. But in gas-poor environments, things played out differently. These regions were less dense, further from the filaments of the cosmic web, or disturbed by heating processes that prevented gas from condensing in the first place. Without a steady supply of cold gas, galaxies in these areas struggled to assemble enough mass to trigger consistent star formation. The reionization era, which happened between 500 million and 1 billion years after the Big Bang, is a key example of this reduction. During this time, the first galaxies and stars sent out very strong ultraviolet light that made the hydrogen in the intergalactic medium charged again. Low-mass halos are small areas of dark matter that are trying to gather gas and make stars. That high-energy light destroyed them. The UV light cooked the gas, which raised the pressure and made it harder for gravity to pull it in. Some halos lost all of their gas before their galaxies could even start. As a result, many small galaxies were effectively aborted. They remained dark, invisible to telescopes, and filled only with dark matter, and possibly some leftover ionized gas. These systems may account for a significant portion of the so-called missing satellites problem, the gap between the predicted number of dark matter halos and the fewer number of dwarf galaxies we actually observe around galaxies like the Milky Way. Even beyond reionization, gas availability varies based on cosmic environment. Galaxies in dense clusters often suffer from a process known as ram pressure stripping. As a galaxy moves through the hot, X-ray emitting plasma that fills a cluster, that external pressure can strip away its cold gas like wind ripping leaves from a tree. The galaxy might survive structurally, but its star formation shuts down, leaving it to fade into a red dead shell of its former self. Separated galaxies in the cosmic gaps, which are the vast, less dense parts of the universe, on the other hand, tend to keep their gas for a much longer time. These galaxies can keep making stars regularly for billions of years because they don't have to deal with many interactions, weaker tidal forces, or environmental damage. In these quiet parts of the universe, galaxies that are still fed by slow but constant streams of cold hydrogen are some of the bluest and most star-forming ones that have been seen so far. This difference also helps to explain why galaxy development paths are so different. A gas-filled dwarf star may burst into flames in a violent flare, making stars very quickly before being blown out by supernova winds. In contrast, a large galaxy that is low in gas may never start star formation again, even if it merges or absorbs other galaxies. This is because the environment has become so hot or drained that nothing new can collapse. The amount of metal in gas-rich and gas-poor processes is also different. Through stellar nucleosynthesis, galaxies that keep making stars add heavier elements to their gas over time. Gas-poor galaxies, on the other hand, might never have any metals because they don't make many new stars, so they don't dirty the space between the stars. This low metallicity makes it even harder for things to cool down and for stars to form, which keeps the universe poor. The galactic mass function, which is a statistical breakdown of galaxy sizes, also gives us an idea about how gas abundance might affect things. There are a lot more galaxies with lower masses, but not as many that shine. Many of them are weak, do not move, or behave irregularly because they can't hold on to or get enough gas. Most of the bright galaxies in the universe are high-mass ones that were formed in gas-rich environments or gain mass through mergers. The role of cosmic reionization. In the early days of the world, light couldn't go very far. Around 370,000 years after the Big Bang, the universe cooled down enough for protons and electrons to join together to form neutral hydrogen atoms. This is called recombination. The cosmic microwave background, a picture of a dark, dense universe, was made at this time. It wasn't quiet for long, though. After some 300 million years, something amazing took place. The first galaxies and stars began to shine. Their energy changed the chemistry of the world in a basic way, not just making it brighter. This was the time of cosmic reionization, which was a major turning point in the history of the galaxy. Cosmic reionization refers to the period when ultraviolet radiation from the earliest sources, massive stars, quasars, and galaxies, reionized the neutral hydrogen that filled the universe. That means the atoms were stripped of their electrons again, transforming the universe from a cold, neutral fog into a hot, ionized plasma. But this wasn't some instant transformation. It was messy, patchy, and had huge implications for where and how galaxies could form. The timeline goes something like this. By about 400 million years after the Big Bang, early galaxies were already producing high-energy ultraviolet photons. These photons began carving out ionized bubbles in the neutral hydrogen around them. Over the next several hundred million years, these bubbles grew and merged, eventually overlapping to fill the cosmos. By around 1 billion years post-Big Bang, the universe was mostly transparent again. What does this have to do with how galaxies form? Everything. Reionization added a strong type of feedback, which is how galaxies change their own surroundings. As soon as the cosmic medium got charged again, it got hot, and it often got above 10,000 Kelvin. This was terrible for small halos. These young dark matter spots, which had masses of less than 10 to the 9th solar masses, depended on their gravity to pull in cool neutral gas. But when that gas became charged and hot all of a sudden, it built up enough pressure to keep from falling apart. A lot of these halos were either completely devoid of gas or couldn't gather enough matter to start star formation. This means that reionization stopped the birth of many galaxies in low-mass halos before it could start. This explains part of the missing satellites problem, why we don't see nearly as many small galaxies around the Milky Way as predicted by dark matter simulations. Some of those halos probably exist, but they remain dark and starless, stunted by reionization. We have observational hints of this suppression in ultra-faint dwarf galaxies. Some of these dim systems contain ancient stars that seem to have formed before, or just as reionization began and then abruptly stopped. Their star formation histories look like cliff edges, a brief burst followed by silence. These galaxies might be fossils from the reionization era, survivors of a cosmic event that snuffed out others like them. Reionization didn't just erase potential galaxies, it also shaped the evolution of the galaxies that did survive. In areas where reionization occurred early, often dense, clustered regions, the intense radiation field could sterilize neighboring halos before they could form stars. This led to a bias. Galaxies in these regions evolved faster and became more massive, while those in quieter, later ionizing regions developed more gradually. The Lyman alpha forest, a pattern seen in the spectra of distant quasars, gives us insight into this process. It reveals the distribution of neutral and ionized hydrogen along the line of sight, letting astronomers map how the universe's transparency changed over time. This mapping helps determine when reionization occurred in different regions, confirming that it wasn't uniform. Even more interesting is how reionization might have kept some galaxies failing over and over again. Some halos had just enough matter left over after they lost their gas to make a few stars. These stars gave off radiation and burst as supernovae, which fed back into the system and heated up any gas that was still there even more. These systems turned into cosmic ghosts because they didn't have enough mass to hold on to their matter. They were visible in models, but not in the night sky. Reionization also affects metallicity. Since it shut down star formation early in many small halos, those galaxies never enriched their gas with heavier elements. As a result, some of the lowest mass galaxies observed today are extremely metal poor, echoing the chemical conditions of the early universe. Another interesting thing is that reionization might have been different in different places. Early galaxies that were making stars put out more UV light in areas with more matter, which made early reionization zones. But cosmic gaps, which are places with fewer galaxies, were ionized later. This gave halos more time to form there before the heating wave hit. Based on where a galaxy lived during reionization, it may or may not have formed at all. Recent observations from the James Webb Space Telescope are shedding more light, literally, on this era. It has detected bright, massive galaxies at redshifts of 10 or higher, suggesting that some galaxies formed and began altering their environments incredibly early. These objects likely played a central role in kicking off reionization. However, we've also found potential evidence of smaller galaxies existing just before or during this transition, offering a glimpse of the types that may have been wiped out or suppressed shortly thereafter. Reionization has left a lasting mark. It made a cosmic screen that chose which galaxies would be able to stay alive and grow. Even though it seems like a long time ago, its effects can still be seen in the way galaxy masses are distributed, the lack of low luminosity systems, and the strange behavior of ultra-faint dwarfs. Ultra-diffuse galaxies and failed giants. Not every galaxy is a brilliant light show. Some don't shine at all, but they are huge and stretch across the sky. These are ultra-diffuse galaxies, or UDGs. They are some of the weirdest and least sense-making shapes in the universe. Think about a galaxy the size of the Milky Way that has 1% of the stars. That's why UDGs are so scary. They are huge, ghostly clouds of stars that are so dim that you can almost miss them, and so thick that scientists can't figure out what they are. The discovery of UDGs isn't entirely new, but their numbers and diversity have only become clear in the past 2 decades. In 2015, a team using the Dragonfly telephoto array, an instrument designed specifically to detect low-surface brightness galaxies, revealed dozens of these ethereal giants in the Coma cluster. Each of them spanned tens of thousands of light-years, rivaling large spiral galaxies in diameter. But they contained 100 to 1,000 times fewer stars. They shouldn't exist, or at least not in this quantity. Right away, someone asked, how did something so big get so empty? One idea is that UDGs are galaxies that failed. It's possible that they were born with enough dark matter to build a big structure and store gas, but they never made many stars. They may have lost their gas early, possibly because of reionization or effects of the surroundings. Or maybe the blowback from a few very powerful supernovae burned up all the gas they had. Their growth stopped before they could shine no matter what. Their dark matter halos give us a clue. With mass-to-light ratios higher than 100, some UDGs look like they are mostly made up of dark matter. This makes sense in clusters like Coma, because the galaxies there need big halos to survive the strong tides that come from being so close together. Dark matter holds them together, or they would have been torn apart without it. But some UDGs that are not in groups don't seem to have this safety, which makes me wonder how they stay together. Another theory suggests that UDGs formed with extremely high angular momentum. In this view, they started with a generous helping of gas and dark matter, but their initial spin was so fast that the gas stretched out into an unusually extended disk. This thin, fragile structure prevented the gas from collapsing efficiently, leading to sparse star formation. In other words, they're not failed galaxies, they're just slow cookers, taking their time and spreading their material thin. Observations from telescopes like the Hubble Space Telescope and Keck Observatory have helped distinguish between these possibilities. Some UDGs, for example, contain globular clusters, dense star clusters typically found in massive galaxies. The number of these clusters often correlates with the host galaxy's total mass. In several UDGs, the globular cluster population suggests a surprisingly massive dark matter halo, implying that these ghostly systems may be heavyweights in disguise. That led to the hypothesis that some UDGs are stripped-down giants, once vibrant galaxies that lost their gas and stars due to environmental interactions. If a massive galaxy passes close to a cluster's center, or a larger neighbor, tidal forces can peel off its outer stars and gas, leaving behind a dim core that still spans a wide area. This process would explain UDGs in dense clusters, but fails to account for their presence in isolation. Some UDGs question every plan. Astronomers using the Dragonfly array found a UDG called NGC 1052DF2 in 2018 that didn't seem to have much dark matter. That really shocked me. If it's true, it goes against decades of research that said galaxies can't form or stay together without dark matter. DF2 was about the same size and brightness as other UDGs, but when scientists watched how its star groups moved, they saw that almost all of the galaxy's mass came from matter that could be seen. This finding caused a lot of heated discussion. Did the reading come out wrong? Or had we found a different kind of galaxy? A follow-up discovery, NGC 1052DF4, showed similar properties: low stellar content, large size, and negligible dark matter. These findings suggest that some UDGs may have formed through unusual tidal processes, where galaxies are stretched and stripped during close interactions, leaving behind puffy remnants with little to no dark matter. These darkless UDGs may be tidal ghosts, born not from slow evolution or failed growth, but from violent cosmic encounters. The diversity of UDGs is the key takeaway. They aren't a single class of object with a single origin. Some may be failed giants. Others may be flukes of angular momentum or star formation efficiency. Still others may be battle-scarred survivors of galactic collisions. But all of them push the limits of how we define a galaxy. They're too faint to fit comfortably with normal spirals or ellipticals, and too large to be classified alongside dwarf galaxies. In a lot of ways, UDGs test our ideas about how galaxies form. If polls show that these systems are common, then our models need to show how big, dim systems can form and stay in place in different settings. This is very important because it calls into question what we thought we knew about how mass, light, and structure are connected in the world. How cold streams fuel high redshift galaxies. Most galaxies grow slowly in the universe we live in now. They take in gas from the space between galaxies, reuse material from supernovae, and sometimes they eat one of their neighbors. But some galaxies grew very quickly in the early universe, especially in the 3 billion years after the Big Bang. The question is how they kept the star shape going for so long without running out of fuel. What's the answer? Cold water flows. Big, clear streams of hydrogen that cut through space and brought fuel straight to the centers of galaxies. To understand why cold streams matter, you need to first consider how galaxies normally gain mass. In the classical model, gas falls into a galaxy's dark matter halo, hits a shock boundary, heats up to the halo's virial temperature, and slowly cools before forming stars. This process takes time, sometimes hundreds of millions of years. But for early massive galaxies, that timeline doesn't add up. Observations have shown enormous star-forming galaxies, some churning out hundreds of stars per year, already existed when the universe was less than 2 billion years old. Something faster had to be in play. That's where cold accretion streams enter the picture. Simulations in the early 2000s, especially those using high-resolution cosmological hydrodynamics codes like Ramses and Arepo, revealed a surprising alternative to shock heating. If gas enters a galaxy's halo along narrow, dense filaments from the cosmic web, it can bypass the heating process entirely. These streams dive straight into the galaxy at temperatures of around 10,000 Kelvin, cold by cosmological standards, and deliver gas directly to the central regions. What makes these cold streams possible is the interplay between the mass of the galaxy and the temperature of the incoming gas. In low-mass halos, gas is not compressed enough to shock, but in more massive halos, those with a total mass between 10 to the 11th and 10 to the 12th solar masses, you'd normally expect shock heating to dominate. However, if the incoming filament is narrow, dense and moving quickly, it can maintain its coherence and temperature all the way through the hot halo medium. Think of it like a fire hose punching through a cloud of smoke. It stays intact long enough to get to the core. It is hard, but not impossible, to get direct observational proof for cold streams. Some of the most useful clues come from Lyman alpha blobs, which are huge bright clouds of hydrogen gas seen at very high redshift. These patterns, which can be over 200,000 light-years long, may show where cold gas joins a galaxy and gets just hot enough to give off ultraviolet light. Also, studies of quasars, which are places where galaxies in the center leave their gas fingerprints on the light of objects in the background, have found narrow, cool absorption features that match the behavior of cold gas flows that move quickly. Even more convincing are simulations that match what we know about galaxies during the cosmic noon, the time when stars were forming the most, which happened about 10 billion years ago. At this point in time, galaxies, especially those with a lot of stars and a lot of star formation going on, seem to need a steady flow of cold gas to explain their light and makeup. Models that don't have cold flows either heat the gas too much or don't make enough stars. The power of these streams lies not just in their volume, but in their efficiency. Cold accretion delivers gas to where it's needed, fast and focused. Instead of hanging out in a halo for 1 billion years, the gas arrives in tens of millions of years, condenses, and forms stars almost immediately. In some simulations, the inflowing cold streams even align angular momentum in such a way that they spin up protodisks, giving rise to early rotational structures long before spirals were expected to form. But cold flows don't last forever. As halos get bigger, above 10 to 12 solar masses, they start to make stable shocks that stop the streams before they can reach the center. This change from shock to warmth cuts off the cold supply, so galaxies have to use slower, less efficient processes. This could be one reason why some galaxies stop making stars after a certain point. When the cosmic fire hose stops, the stars stop forming. There's also growing evidence that cold flows may shape metallicity gradients in young galaxies. Because the inflowing gas is pristine, largely devoid of heavy elements, it can dilute the central regions, leading to low metallicity cores. This is the opposite of what we see in many local galaxies, where the outskirts are metal poor and the centers are enriched. That flipped gradient is a telltale sign of early cold accretion. Some big telescopes, like the James Webb Space Telescope and the 30-meter telescope, will soon be able to see these rivers better. Astronomers want to be able to see high redshift galaxies in more detail than ever before, so they can directly track the inflows and see how gas swirls in to feed starbursts and build up the disks and bulges of young galaxies. Why the first disks are so hard to explain? Most theories about how galaxies form say that disk galaxies like the Milky Way form in a slow, orderly way. Gas falls apart because of gravity, keeps its angular momentum, cools, and spreads out into a spinning circle that stars are slowly forming on top of. There is a catch to that story, though. It takes time, a lot of it. Astronomers were shocked by the first pictures taken by cameras like Hubble and ALMA because of this. They showed that big, well-formed disks were around just 1 billion years after the Big Bang. That's only about 10% of the way through the universe's current age. Traditional models say that those disks shouldn't have had time to form. How did they get there? To solve the puzzle, you must first look at how the world was in the beginning. The universe went through its dark ages after recombination, when neutral hydrogen formed and photons could move around easily. This was before stars, galaxies, or any other complex structures had formed. During this time, gravity caused matter to start to stick together, which started as small changes that would eventually turn into halos of dark matter. These halos were the building blocks for galaxies to come. Now, in theory, baryonic matter, normal gas, would follow the dark matter, fall into those halos, and eventually cool and settle into disks. But the early universe wasn't gentle. It was chaotic, with high densities, intense ultraviolet radiation from reionization, and frequent mergers. Simulations suggested that most early galaxy progenitors should be messy, clumpy, and irregular. The process of settling into a clean rotating disk was expected to take several billion years, long after the chaotic merger era. But when scientists looked into the faraway universe, they saw something they didn't expect. Long, smooth disks that were rotating. Some of them were already turning into stars at very fast rates, but their motion stayed steady. This was the exact opposite of what the models said would happen. In one study, using the Atacama Large Millimeter Submillimeter Array, ALMA, the Wolf disk, a spinning disk in galaxy DLA 0817G, was found at redshift 4.26. This means it existed when the universe was only 1.5 billion years old. Over 30,000 light-years across, the disk looked like it was moving steadily in a circle. It wasn't a fluke when that was said. Similar things were seen in other disk galaxies with high redshift. Some early galaxies were already organized and pretty calm, so they weren't like crazy train wrecks. There was a big problem with these kinds of systems. How could disks form so quickly? How could they keep things in order in a time when everything was chaotic? Scientists have come up with an idea about cold accretion streams, which are rivers of pure hydrogen from the cosmic web that feed galaxies without heating the gas up too much. These streams could bring in a regular flow of low angular momentum matter, which would speed up the spinning of gas and make it flatten out faster than predicted. It's also possible that cold streams can help stop the instability that would otherwise break up the gas into groups or be messed up by feedback from early starbursts. Another factor is the mass threshold of the host dark matter halos. Massive halos can stabilize gas faster, allowing it to settle into rotational motion despite the violent cosmic conditions. Moreover, high gas fractions in the early universe meant there was more material to dampen perturbations. Essentially, if a galaxy formed in a large enough well of dark matter and had access to smooth cold gas inflows, it might short-circuit the messy early phase and go straight to disk mode. Still, there's tension between simulation and observation. Even the best cosmological models, like Illustris, Eagle, or Fire, struggle to produce stable disks at such early epochs. When they do form disks, they're often too thick, too turbulent, or too short-lived. Fine-tuning the feedback, gas cooling, and merger histories can help, but it's a delicate balance. A bit too much supernova feedback, the disk gets blown apart. Too little, it fragments into unstable clumps. There's also the matter of dust and clarity. Some galaxies may look like disks, but that's just because of how the light is spread out. The gas and stars aren't moving in a straight line. But high-resolution spectroscopy from devices like MUSE and ALMA has shown that at least some of these galaxies do have rotation curves. These are velocity profiles that show how the gas in the galaxy spins in a disk-like pattern. The presence of early disks also complicates our understanding of galaxy evolution. If disks formed early and efficiently, then some of the spirals we see today may be the quiet survivors of a very dynamic youth. That means the classic picture of irregulars becoming ellipticals via mergers and ellipticals settling into spirals might be oversimplified. In reality, disks may have emerged in parallel with other structures and persisted through different evolutionary paths. More than that, early disks make us rethink what disturbance does. In high redshift galaxies, turbulence may not have been a problem. Instead, it may have helped keep things stable by spreading out rotational momentum and making it easier for disks to form in a more unstable environment. Newer computer models show that turbulent pressure and high gas accretion rates might be able to survive with ordered rotation. This could cause thick, clumpy rings to form that are still spinning. Dark galaxies, no stars, just gas and halo. Envision a galaxy that is so hard to find that it barely shines. Not because it's covered in dust or fog from space, but because it never lit up in the first place. These are dark galaxies, the ghostly things that exist in space. No bright stars, no twisting arms that sparkle. It's just clouds of gas floating through space without making a sound. For decades, they were just a thought experiment. They are more and more of an observed puzzle these days. The idea of dark galaxies emerged from simulations that showed many small dark matter halos forming early in the universe. If every halo became a galaxy filled with stars, we'd see far more galaxies than we do. But there's a mismatch. For every bright galaxy, simulations suggest there should be dozens, even hundreds of smaller dark matter halos. So, where are they? One answer: some halos never formed stars at all. They remained dark, unlit, ghostly. These dark galaxies, if they exist, would still interact with gravity. They'd warp space. They'd tug on visible matter. But they wouldn't emit their own light, making them extremely difficult to detect. It's like trying to find fog in the night sky, by how it blocks out stars behind it. In 2012, a team using the Very Large Array Radio Telescope in New Mexico discovered a curious object in the Virgo cluster, later dubbed Virgo High 21. It had a signature of neutral hydrogen gas, known as HI, but showed no signs of star formation. No optical counterpart, just gas. The radio data suggested it was rotating, indicating the presence of a dark matter halo. Was this the first dark galaxy ever seen? Some people said it might just be a tidal tail, which is gas that was ripped off of another galaxy by gravity. But the fact that it didn't look like the shapes or flows of tidal garbage meant that the chance was still there. A few more prospects showed up. The Dragonfly telephoto array found dozens of very faint galaxies in the Coma cluster in 2016. A lot of them had stars, but not many. Some were so weak that earlier scans couldn't even see them. Dark galaxies, which are ones that don't have any stars at all, are still rare and debatable. Part of the trouble is that it's very hard to be sure that a galaxy has no stars. From the infrared to the ultraviolet, you'd have to look for starlight in every type of light and still not find it. It's more likely that you can find their gas. Surveys of the early universe using instruments like ALMA and the Green Bank telescope have picked up HI signals with no matching optical detections. These signals could be gas-rich halos where star formation never kicked off. Why wouldn't they form stars? One explanation lies in the cooling inefficiency of small halos. In low-mass systems, gas may never reach the densities or low temperatures needed to spark star formation. If the gas can't cool, it can't collapse. No collapse, no stars. Cosmic reionization may have also played a role. After the first stars and galaxies lit up the universe, their ultraviolet radiation flooded space, ionizing hydrogen and heating it up. This could have prevented small halos from ever trapping gas again. Starless galaxies might be fossils of this cosmic shutout. The role of explosion feedback is also important. If one or two stars do form inner halos, those early blasts might be enough to blow out the rest of the gas and stop star formation for good. What's left is a dark skeleton, which is made up of a ring of dark matter and maybe some drifting gas. But maybe the most tantalizing hint of dark galaxies comes from gravitational lensing. In 2018, researchers analyzing lensing distortions around massive galaxies found subtle anomalies that couldn't be explained by visible matter alone. These wiggles in space-time suggested the presence of small dark objects with mass. Potentially dark galaxies. They bent light but didn't shine. And they were exactly where simulations said they should be. So why do we care about dark galaxies? They could be the missing piece in theories of how galaxies form. A lot of them would help solve the missing satellites problem, which is why we see fewer dwarf galaxies than models say we should. A lab is also available to test ideas about dark matter. If some kinds of dark matter stop stars from forming, then the presence or lack of dark galaxies could support or refute those ideas. In the future, tools like the Vera Rubin Observatory and the Square Kilometre Array may make things clearer. Because they can pick up on weak signs and cover large areas, they may finally find a group of dark galaxies. Lots of them, not just a few. What determines the maximum size of a galaxy? Galaxies come in many forms and sizes, from dwarf galaxies that are only a few million light-years across to IC 1101, a titanic giant with a width of over 6 million light-years. Still, there's the question, is there a cap? A limit in space or time to how big or heavy a galaxy can get? Where are the galaxies that are hundreds of millions of light-years across and filled with quadrillions of stars that we can see? And it turns out that galaxies can only grow so big. The limits are built into the physics of the universe. Before we can understand this roof, we need to look at the building blocks, gas, dark matter, and the space-time fabric in which they work. The dark matter halos are where galaxies are born because they have a lot of gravity. More gas can be drawn to a cloud that is bigger. But this process can only go so far. When a halo gets bigger than a certain mass, around 10 to 12 solar masses, the gas dropping into it gets shocked and heated to very high temperatures. This makes it much harder for the gas to cool down and form into stars. If it doesn't cool down, gas just stays in hot halos and can't fall and start a star from nothing. This effect becomes even more extreme in halos around 10 to the 13th or 10 to the 14th solar masses. At these scales, galaxies tend to stall. Instead of growing via cold gas accretion, they start evolving through mergers. These mergers can add mass, but they also tend to heat up and disrupt existing structures, making it harder for galaxies to grow in an orderly, star-forming way. Environmental issues are another problem. Most of the largest galaxies we see, like the center galaxies in groups, are destroyed by their own gravitational pull. They are in areas that are thick and full of hot plasma, which strips gas away or makes it unusable in some other way. Little galaxies often arrive already out of gas and fuel, even if they fall in and join. Feedback from supermassive black holes also plays a key role. As galaxies grow, Their central black holes tend to grow in tandem. These black holes, especially when actively accreting material, release powerful jets and winds that can heat and eject gas from the galaxy. This feedback loop effectively shuts down star formation in the largest galaxies, locking them into a passive, aging state. The black hole doesn't need to eat the whole galaxy. It just needs to blow away or prevent the gas needed for growth. You should also think about a moving limit. As galaxies get bigger and more stars, they are more likely to become unstable. Massive galaxies can get so crowded that internal gravity interactions start to rearrange energy and rotational momentum in a very disorganized way. These interactions include bars, disk instabilities, and violent relaxation. Over time, these effects can make disks flatter, bulges bigger, and stars spread out into hazy halos, which makes organized growth less effective. Observations back this up. Studies of galaxy populations in large-scale surveys like the Sloan Digital Sky Survey and the Galaxy and Mass Assembly Project show that star formation rates plateau or even decline past a certain mass threshold. Galaxies above about 10 to the 11 solar masses show a dramatic drop in star-forming activity, regardless of how much gas they might still contain. The bigger they get, the quieter they become. And then there's the black hole clock. There have been 13.8 billion years since the beginning of time. It's been a long time, but not that long. There hasn't been enough time for a galaxy to grow forever, even if all the circumstances were right. It takes billions of years for the universe to form structures, and as it ages, the building blocks it needs become more spread out and harder to get to. Not just nearby, but all over the universe, galaxies are running out of fuel. Space-time is expanding faster than ever because of dark energy. This stops growth again. As the universe expands faster and galaxies move farther apart, they join and engage less often. In the end, galaxies will be stuck in their own cosmic boxes, with no more coming together or colliding. There will only be dimming stars and darker skies. The maximum size of a galaxy is governed by multiple converging limits: cooling inefficiencies, environmental suppression, feedback from black holes, internal instabilities, time constraints, and the very expansion of the universe itself. It's not one cap, it's a layered system of breaks that collectively say, that's big enough. IC 1101, the current record holder for galaxy size, is already a statistical anomaly. It lives at the center of a massive cluster, has absorbed dozens of smaller galaxies, and exists in a rare confluence of favorable conditions. Galaxies bigger than this are not just rare, they might be fundamentally impossible in our universe's current framework. Thanks for joining us on our journey into the unknown. Don't stop here if you want to learn more about our place in the universe, and your mind has been pushed a little further. If you subscribe for Beyond Horizons, we'll talk more about the strange, beautiful, and unsolved questions of space. Since the universe never ends, and your interest shouldn't either.